Hello there, and welcome to Life Beyond Seen, where the deepest questions often come wrapped in the deepest quiet. Imagine for a moment that depth is not just a measurement, that it is something closer to distance, not across a map, but away from everything familiar, away from light, away from warmth, away from the sounds that fill our days. Every meter downward is another step into a world that operates by entirely different rules, where the pressure of an entire ocean column presses in from every direction, where the temperature hovers just above freezing and has for millions of years, where nothing from the surface, not sunlight, not weather, not the noise of ships, reaches in any meaningful way. At a certain depth, the ocean stops feeling like water and starts feeling like something else entirely. Something that has its own logic, its own patience, its own long and largely unwitnessed history. Tonight, we are going to talk about a place that most people have never heard of. Not the Mariana Trench, which has become something of a household name over the last few decades. Not the Puerto Rico Trench, which holds the deepest point in the Atlantic. This is a different place, quieter in the public imagination, less visited even by the scientific community, and in many ways more unknown than either of those more famous names. It runs for roughly 1,000 kilometers through the western Pacific Ocean, beginning not far south of Tokyo Bay and curving southward toward the volcanic arc that eventually connects to the Mariana system. It reaches depths of around 9,780 meters at its deepest recorded point. It sits at the edge of what human technology can reliably reach, and it almost certainly contains living creatures that no human being has ever seen. This is the Ogasawara Trench. Before we go any further, I want to ask you something simple. Where are you right now? Are you at home, tucked in for the night, listening with the lights already off? Maybe you are somewhere else entirely. A different country, a different time zone, a different kind of evening. Maybe it is the middle of the afternoon where you are, and you just needed something calm to listen to while you work. Whatever the case, I am glad you are here. This is the kind of topic that rewards a little stillness, the kind of story that opens up more the slower you take it. And if you enjoy what we do here at Life Beyond Seen, the slow, careful, late-night kind of exploration, it genuinely helps to leave a like on the video, or to subscribe if you have not already. It keeps this channel going, and it helps other people find these kinds of stories when they need them. Alright, now let us go somewhere very far down. The Ogasawara Trench, sometimes written as the Bonin Trench, the two names referring to the same feature from slightly different reference points, is one of the great structural scars of the Pacific sea floor. It is not a random crack or a simple valley. It is the surface expression of one of the most powerful geological processes on Earth: subduction. Two of the planet's tectonic plates are meeting here, and one of them is losing. The Pacific plate, moving slowly westward, is being forced downward beneath the Philippine Sea plate at a rate of roughly 2 to 4 centimeters per year. That sounds slow, and by any human measure it is. But over millions of years, that movement has carved out a trench of extraordinary depth and extraordinary length, and it continues to carve it now, at this very moment, while you are listening. The trench itself runs roughly north to south, beginning somewhere around 32 or 33 degrees north latitude, which puts its northern end in the general vicinity of the Izu Peninsula, southwest of Tokyo, and extending southward for approximately 1,000 kilometers until it begins to merge with the broader Mariana Arc system. Along the way, it passes beneath and alongside the Ogasawara Plateau and the Bonin Island chain, a scattered group of volcanic islands that includes Chichijima and Hahajima, both of which are real, inhabited places with their own histories, their own communities, their own ferry routes from Tokyo. The islands sit above a geological system of enormous power, though you would not necessarily know it standing on their shores watching the ocean. The deepest confirmed point in the Ogasawara Trench sits at around 9,780 meters below sea level. Some sources round this to approximately 9,800 meters, depending on the survey method used. To put that in terms that are a little easier to picture, if you placed Mount Fuji, Japan's tallest peak, standing at 3,776 meters, into this trench, it would disappear completely, with more than 6 kilometers of water still above its summit. The trench is not just deep. It is deep in a way that makes the word feel inadequate. And yet, despite all of this, despite its length, its depth, its geological drama, and its proximity to one of the most densely populated coastlines in the world, the Ogasawara Trench remains largely unknown to the general public. Ask most people to name a deep ocean trench, and they will say the Mariana. Some might say the Puerto Rico Trench. A well-read person might mention the Kermadec Trench near New Zealand, or the Tonga Trench, which is actually the second deepest in the world. But the Ogasawara Trench, it rarely comes up. It does not have a famous dive associated with it. It has not appeared in many documentaries. It has not had a celebrity submersible expedition broadcast to millions of viewers. There is something quietly strange about that, when you think about it. Here is a feature that runs for 1,000 kilometers through the ocean, that reaches nearly 10 kilometers in depth, that sits in the backyard of one of the world's most technologically advanced nations, and it remains, in most practical senses, unknown. Not because no one has tried to study it, not because science has ignored it, but because the deep ocean is simply that difficult to reach, that expensive to study, and that vast in proportion to the tools we have built to understand it. The Western Pacific in general is one of the least explored ocean regions on the planet. That might seem surprising given how much of human civilization has developed along its edges. Japan, the Philippines, Taiwan, the Mariana Islands, countless smaller territories and communities. But the ocean's surface and its depths are almost entirely separate worlds, and what happens on the surface tells you very little about what is happening 9 kilometers below. The Western Pacific's Hadal zones, the term used for ocean regions deeper than 6,000 meters, include some of the deepest water on Earth, and collectively they remain almost entirely unsampled. The Ogasawara Trench is one of the larger and deeper of these zones, and its exploration history is thin in a way that is almost uncomfortable to acknowledge. What we do know about this trench comes from a combination of acoustic mapping, sediment cores, and a relatively small number of lander deployments, free-falling instrument platforms that descend to the seafloor, record what they can, and then release ballast weights to float back to the surface. Japan's National Ocean Research Agency, JAMSTEC, the Japan Agency for Marine Earth Science and Technology, has done the most sustained scientific work in this region, and their expeditions have given us the clearest picture we currently have of the trench's geography and biology. But even that picture is fragmentary. The trench is long, and the number of points where samples have actually been collected is small. There is something almost counterintuitive about this situation. We live in an era of extraordinary technological capability. Satellites map the surface of Mars at resolutions of a few meters per pixel. Telescopes peer back to within a few 100 million years of the Big Bang. We have sent probes to the edges of the solar system past Pluto into interstellar space. And yet here, on our own planet, less than 10 kilometers below the surface of an ocean that covers more than 60% of the Earth, there are places we have never seen, creatures we have never encountered, biological and chemical processes we can only guess at. The Ogasawara Trench is one of those places. It is not at the edge of the universe. It is roughly 2 hours by plane from Tokyo. Part of what makes this trench worth understanding, really understanding not just as a name on a map, is its relationship to the broader geography of the Pacific. The Izubonin-Mariana Convergent Margin, of which this trench is a part, is one of the oldest and most active subduction systems on Earth. The Pacific Plate has been diving beneath the Philippine Sea Plate for tens of millions of years along this boundary. The process has built island arcs, fueled volcanoes, triggered earthquakes of enormous magnitude, and carved a series of deep trenches into the ocean floor that collectively represent some of the most extreme environments on the planet. The Ogasawara Trench is not an isolated feature. It's part of a connected system that stretches from near Japan all the way south to Guam and beyond. A continuous geological story written in stone and water and pressure. But within that system, the Ogasawara Trench has its own character. Its walls, its sediment, its chemistry, its biology. These are not simply copies of what you would find in the Mariana Trench a few hundred kilometres to the south. Trenches are isolated environments. The abyssal plains that separate them act as barriers for many deep-sea organisms. Species that evolve in one trench may never reach another. The conditions in each trench, the food supply, the chemistry, the geological activity, the sediment type, shape the life that develops there in ways that are specific to that place, which means that whatever lives in the Ogasawara Trench may be found nowhere else on Earth. That is not speculation. That is how Hadal biology appears to work based on the evidence gathered so far from other trenches. And it makes the Ogasawara Trench not just an interesting geological feature, but a biological territory unto itself. One that has had millions of years to develop its own inhabitants, its own ecological relationships, its own evolutionary paths, in near total isolation from the rest of the ocean, and certainly from any human observation. The trench is there right now. It has been there for tens of millions of years. Its deepest points have never been visited by any human-operated vehicle. Its walls have never been photographed in any comprehensive way. The creatures that live in its Hadal depths, below 6,000 metres, have been glimpsed only in the most fragmentary sense, through baited camera traps and the occasional recovered sample. And there is good reason to believe, based on what we know about how life evolves in isolated deep-sea environments, that among those creatures are species that have never been formally described, never been named, never been studied. Life that exists in a darkness so complete and a pressure so extreme that the human mind struggles to hold the image for long. We're going to spend some time with this trench tonight. We're going to look at what it is, how it formed, what conditions exist inside it, what has been found there, and what almost certainly remains hidden. We will look at the science honestly, separating what is confirmed from what is suspected, what is documented from what is carefully inferred, and we'll try to hold on to something that the deep ocean tends to inspire if you let it, a genuine sense of how much of this world remains beyond the reach of human knowledge. The trench is waiting. It has been waiting for a very long time, and it is not in any hurry. To understand why this place is what it is, why it is so deep, why its walls are shaped the way they are, why the whole region sits in a kind of perpetual geological tension, we need to start with the ground beneath it. Not the seafloor exactly, but what is happening far below that seafloor, in the slow and enormous collision of two of the Earth's great tectonic plates. The Pacific Plate is one of the largest pieces of Earth's outer shell. It covers an area of roughly 103 million square kilometres, and it is moving. Not quickly by any human measure, a few centimetres per year, which is about the rate your fingernails grow, but steadily, relentlessly, in a direction that has not changed in tens of millions of years. Along the western edge of the Pacific, where the plate meets the Philippine Sea Plate, something happens that is as fundamental to the planet's geology as anything that occurs on its surface. The Pacific Plate descends. It bends downward at the contact zone between the two plates, and it begins a slow journey into the Earth's mantle, sinking at an angle of roughly 45 to 60 degrees beneath the Philippine Sea Plate. This process is called subduction, and it is the direct cause of the Ogasawara Trench's existence. The rate of subduction here is estimated at somewhere between 2 and 4 centimetres per year, depending on the specific location along the boundary and the measurement method used. That sounds modest. But over millions of years, 2 centimetres per year accumulates into something immense. The Pacific Plate has been subducting along this margin for somewhere in the range of 40 to 50 million years, possibly longer. The trench itself, the physical depression in the seafloor, is the surface expression of where the descending plate bends away from the overriding plate and begins its downward path. The seafloor on the Pacific side slopes toward the trench axis, then drops steeply as the plate curves under. The result is a long, narrow, asymmetric valley in the ocean floor, with one wall that is steeper and one that is more gradual, running roughly north to south for about 1,000 kilometers. The shape of the trench is not symmetrical, and this is worth pausing on for a moment, because it tells you something about the forces at work. The seaward wall, the Pacific plate side, tends to be less steep, following the curvature of the descending slab. The landward wall, the Philippine Sea plate side, is typically steeper, sometimes dramatically so, because the overriding plate has been pushed and folded by the collision. In between is the trench axis, the narrow strip of seafloor at the very bottom, which at its deepest recorded point reaches approximately 9,780 metres below sea level. That measurement comes from acoustic-sounding data compiled by JAMSTEC and other agencies. It has not been directly verified by a vehicle that physically descended to that depth. The number is reliable within a reasonable margin of error, but it is worth noting that even the depth of this place is known primarily through sound waves bounced off the seafloor from a ship on the surface, not through direct observation. Above the subduction zone, on the Philippine Sea plate side, the geological activity does not stop at the trench. The descending Pacific plate carries water into the mantle, water trapped in minerals, in sediments, in the pores of the oceanic crust itself. As the plate descends and the pressure and temperature increase, this water is released. It rises into the overlying mantle wedge, lowering the melting point of the rock there, and magma begins to form. That magma rises through the crust and erupts at the surface, creating a chain of volcanic islands roughly parallel to the trench. This is the Izu Bonin Arc, sometimes called the Izu Ogasawara Arc, a string of islands and seamounts that includes places like Hachijojima, the Bonin Islands, known in Japanese as the Ogasawara Islands, and the remote volcanic Iwo Jima, or Iwo To, which most people know from the Second World War but which exists in this location because of subduction. The volcanic arc runs roughly parallel to the trench, offset toward the west by the width of the forearc region between them. This arc trench system is part of a much larger geological structure. Continuing southward from the Izu Ogasawara Arc, the same subduction boundary eventually becomes the Mariana Arc and the Mariana Trench. Continuing northward, it connects, through a more complex set of plate interactions, toward the Ryukyu Arc and the geology of southern Japan. The whole system is one of the most geologically active convergent margins on the planet. Earthquakes are common along this boundary, not as background noise, but as the expected and frequent output of two plates locked in a slow-motion collision that releases energy in sudden, violent pulses. Two of the most consequential earthquakes in Japanese history were products of this same geological system. The 1703 Genroku earthquake struck on the 31st of December of that year, with an estimated magnitude of somewhere between 8.0 and 8.2. It was centered in the Sagami Trough, which connects to the broader Izubonin subduction system, and it triggered a tsunami that killed an estimated 5,000 to 10,000 people along the Boso Peninsula and the Sagami Bay coastline. The shaking was felt in Edo, what is now Tokyo, and caused widespread destruction across the Kanto region. The seafloor in Sagami Bay was permanently displaced during this event, with some coastal areas rising by several meters and others subsiding. That kind of sudden vertical movement of the seafloor is a direct expression of the same subduction dynamics that created the Izu Ogasawara Trench. Then there is the 1923 Great Kanto earthquake, magnitude 7.9, centered in Sagami Bay on the 1st of September 1923, at just before noon on a day when cooking fires were lit across the region. The earthquake killed somewhere between 100,000 and 140,000 people. The estimates vary depending on how deaths from the subsequent fires and tsunami are counted. It was one of the deadliest natural disasters in recorded Japanese history. The seafloor of Sagami Bay shifted during this event by several meters in some locations. Sediment was disturbed across a large area. The connection between this earthquake and the subduction of the Pacific Plate beneath the Philippine Sea Plate is well established in the geological record. The same plate boundary that is slowly building the Ogasawara Trench deeper into the earth was also responsible for one of the most catastrophic days in the history of Japan's capital region. These earthquakes are worth mentioning not just as historical events, but because they illustrate something important about the trench. The Ogasawara Trench is not a passive feature. It is not simply a hole in the seafloor that formed long ago and now sits quietly in the dark. It is an active geological structure, part of a system that is constantly in motion, constantly releasing energy, constantly reshaping the seafloor along its length. The plates are moving right now as you listen to this. The Pacific Plate is descending beneath the Philippine Sea Plate at this moment, somewhere between 2 and 4 centimeters per year, and that process is generating stress along the fault zone that will eventually be released in another earthquake. The trench is alive in a geological sense, and that aliveness has consequences for everything that happens within it, including the biology. The long, narrow shape of the trench, roughly 1,000 kilometers from north to south, but only a few tens of kilometers wide at the Hadal depths, is a direct result of this subduction geometry. The plate boundary is essentially linear, and the trench follows that line. As you move along the trench from north to south, the depth changes, the sediment character changes, the distance from the volcanic arc changes. The northern parts of the trench, closer to the Izu Islands and to Japan's main islands, sit beneath waters that are somewhat more productive at the surface. There is more biological material raining down from above. The southern parts, approaching the transition toward the Mariana system, are in waters that are somewhat more oligotrophic, that is nutrient poor at the surface. This gradient matters for what lives in the trench, because almost everything in the deep ocean ultimately depends on what falls from above. The walls of the trench are not smooth. Sonar mapping has revealed a complex topography of ridges, fault scarps, and sediment deposits along the trench walls and floor. Mass wasting events, essentially underwater landslides, have left their marks on the steeper sections of the landward wall. There are places where large blocks of material have broken away and slid toward the trench axis, leaving irregular terrain that would be almost impossible to navigate with a remotely operated vehicle, even if one could reach those depths. The trench floor itself, the narrow axis at the very bottom, is blanketed with fine sediment, a mixture of clay particles that have settled slowly through kilometers of water, and the remains of microscopic organisms from the surface. Diatoms, foraminifera, radiolarians, all reduced to their mineral skeletons and accumulated over millions of years into a soft, unconsolidated layer that records the history of the ocean above. Geologically, the Ogasawara Trench sits within what is sometimes called the Izu-Bonin-Mariana Convergent Margin, and researchers who study this system have noted that it is among the oldest continuously active subduction zones on Earth. The age of the subducting Pacific Plate along this boundary is considerable. The oceanic crust entering the trench here is old, cold, and dense, which is part of why it subducts so readily. Old oceanic crust is heavier than young oceanic crust, and it tends to sink more steeply and more consistently. The slab of Pacific Plate descending beneath the Philippine Sea Plate in this region is thought to extend hundreds of kilometers into the mantle, a long tongue of cold rock slowly being assimilated into the hot interior of the planet. There is something almost difficult to hold in mind about this. The rock that currently sits at the bottom of the Ogasawara Trench, the seafloor at 9,780 meters, formed at a mid-ocean spreading ridge millions of years ago, travelled thousands of kilometers across the Pacific, and arrived at this subduction zone to begin its descent into the mantle. The sediment on top of it accumulated during that long journey, and now it sits at the bottom of one of the deepest places on Earth, under nearly 1,000 times the atmospheric pressure that exists at sea level, in complete darkness, at temperatures just above freezing, waiting to be dragged slowly into the earth over the next few million years. That is the geological context of the trench. Not just a deep place, but a place that is in the process of being consumed. A structure that exists because one plate is swallowing another, and the depression at their meeting point is where the seafloor bends away and begins its long, slow disappearance into the interior of the planet. The trench is, in a sense, a wound in the ocean floor. Not a wound that is healing, but one that is being held open by the continuous motion of the plates. And within that wound, in the darkness and the cold and the enormous pressure of the water column above, something is living. The same geological forces that make this place so extreme are also, in various ways, part of what makes it habitable, or at least survivable, for organisms that have had millions of years to adapt to exactly these conditions. The earthquakes that periodically shake the trench walls send cascades of sediment and organic material down into the Hadal depths. The subducting plate releases fluids that alter the chemistry of the water near the trench walls. The volcanic arc above generates hydrothermal activity that may, in some locations, create chemical gradients that certain organisms can exploit. The geology and the biology of this place are not separate stories. They are the same story, told at different speeds. But before we can talk meaningfully about what lives in the trench, we need to understand what kind of place it actually is to live in. The geological description gives you the shape and the origin of the trench. What it does not fully convey is what it feels like, if feeling is even the right word, to exist at the bottom of nearly 10 kilometers of ocean. The pressure, the cold, the darkness, the chemistry of the water itself. These are not just background conditions. They are the dominant facts of life in the Hadal zone, and they determine at a very fundamental level what kinds of organisms can exist there at all. So let us try to actually go there in some sense. Not physically. No human has descended to the deepest parts of the Ogasawara Trench, and the reasons for that will become clear as we go. But imaginatively, carefully, with the numbers and the physics to guide us, we can try to understand what that environment is actually like. Because the word deep does not begin to cover it. Deep is what you call a lake. Deep is what you call a quarry. What exists at the bottom of this trench is something else entirely, and it requires a different vocabulary. Start with pressure, because pressure is the first thing that would kill you, and it would do so almost instantly. At sea level, the atmosphere exerts a pressure of roughly 1 atmosphere, about 14.7 pounds per square inch. That is the pressure your body has spent its entire existence calibrated to. Descend into the ocean, and pressure increases by approximately 1 atmosphere for every 10 meters of depth. At 100 meters, the depth a very experienced freediver might briefly reach. The pressure is already 10 times what it is at the surface. At 1,000 meters, it is 100 atmospheres. At the bottom of the Ogasawara Trench, somewhere around 9,780 meters, the pressure reaches approximately 978 atmospheres. That is close to 14,000 pounds per square inch. Or, if you want a more physical comparison, it is roughly equivalent to having 50 fully loaded commercial aircraft stacked on top of every square inch of your body. The pressure at that depth does not just crush things, it changes the fundamental behavior of matter. Water itself becomes slightly denser. Chemical reactions that occur normally at surface pressure behave differently. Proteins, the molecular machines that make life work, tend to unfold and lose their function under that kind of compression. The idea of a human being surviving at that depth, without an engineered pressure vessel, is not science fiction danger. It is simply immediate death, in a way that would be too fast to experience. And yet organisms live there, not despite the pressure exactly, but around it, through it, by means of adaptations that took millions of years to arrive at. We will come to those adaptations in a little while. For now, just hold the number. Roughly 900 to 978 atmospheres. That is the environment we're talking about. Temperature at that depth is a different kind of extreme. Not the violent cold of liquid nitrogen, not the dramatic freeze of polar ice. The water near the bottom of the Ogasawara Trench sits at somewhere between 1 and 2 degrees Celsius, just barely above freezing. It has been at roughly that temperature for a very long time, because the deep ocean is essentially thermally stable. The cold, dense water that settles to the bottom of the ocean basins does not warm up or cool down on any timescale that matters biologically. It just sits there, cold and still, year after year, decade after decade, century after century. For organisms adapted to it, this is not a hardship. It is simply the condition of existence. But it does slow things down. Chemical reactions proceed more slowly at low temperatures. Metabolisms run at a lower rate. Growth is slower. Reproduction is slower. Everything is slower. And in that slowness there is a kind of patience that surface life rarely has to develop. Light, or rather the complete absence of it, is the third defining condition. Sunlight penetrates the ocean to a depth of roughly 200 meters under ideal conditions. Clear water, direct overhead sun. Below 200 meters, there is no photosynthesis. Below about 1,000 meters, there is effectively no light at all from the surface. The Hadal zone, defined as depth below 6,000 meters, exists in absolute, total, permanent darkness. Not the darkness of a room with the curtains drawn, not the darkness of a cave where your eyes eventually adjust and begin to pick up something. Nothing. No photons from the sun have ever reached the floor of the Ogasawara Trench. The only light that exists down there is bioluminescence, light produced by organisms themselves, and even that is patchy, intermittent, and not well understood at Hadal depths. For the most part, the trench floor is a world where vision, in the way we understand it, is largely irrelevant. Organisms that live there have adapted accordingly. Some are blind, some have enormous light-gathering eyes sensitive to the faintest traces of bioluminescent glow, and some have essentially abandoned visual information entirely in favour of chemical and mechanical sensing. The Hadal zone itself, that designation for depths below 6,000 meters, is worth pausing on for a moment. The ocean is commonly divided into zones based on depth, and most people are familiar with the broad categories: the sunlit zone near the surface, the twilight zone below that, the midnight zone deeper still, and then the abyssal zone covering the deep ocean floor. The Hadal zone is below all of these. It exists only in trenches, the narrow, elongated depressions formed at subduction zones and transformed faults. Globally, Hadal environments make up a very small fraction of the ocean floor by area, but they represent the most extreme conditions the ocean has to offer. The Ogasawara Trench enters Hadal territory somewhere around the 6,000 metre contour, and its deepest recorded point is nearly 4,000 metres below that threshold. That additional depth matters. The difference between 6,000 metres and 9,780 metres is not merely a larger number. It represents a significant increase in pressure, a slight further decrease in temperature, and an environment that is meaningfully more extreme than the upper Hadal zone in ways that affect what can survive there. Oxygen in the deep trench is perhaps counterintuitive. You might expect that the deep ocean would be oxygen depleted. After all, there is no photosynthesis down there, and oxygen is consumed by respiration. But the Hadal zone is generally not anoxic. The cold water that descends to the deep ocean from high-latitude surface regions carries dissolved oxygen with it, and because metabolic activity at Hadal depths is low, oxygen consumption is slow enough that the water does not become fully depleted. Measurements from deep trenches generally show oxygen concentrations that are low, but not absent, enough to support aerobic life, though not abundantly. There are oxygen minimum zones in the mid-water column above the trench that can be more depleted than the Hadal water itself, which is one of the strange inversions of deep ocean chemistry. The trench floor, in this regard, is not as hostile to aerobic life as you might assume. The sediment at the bottom of the trench is a particular kind of material that has its own character. The finest particles, clay minerals weathered from continents and carried by wind and water across the Pacific, settle slowly through kilometres of water and accumulate on the trench floor over geological time. Mixed in with this clay is what oceanographers call biogenic ooze, the remains of microscopic organisms from the surface ocean, their tiny silica or calcium carbonate shells dissolving or accumulating depending on the water chemistry as they sink. In the Ogasawara region, siliceous ooze, composed largely of diatom frustules and radiolarian tests, is a significant component of the sediment. This fine, soft material blankets the trench floor in a layer that can be several meters thick in places, and it is not simply inert. It contains organic carbon, the chemical energy stored in the remains of surface organisms, and that organic carbon is the primary food source for most of what lives at the bottom of the trench. Not much of it arrives. The journey from the surface to 9,000 meters takes weeks, and most of the organic material is consumed or degraded along the way. What reaches the Hadal floor is a very thin, very dilute rain of nutrition. The sediment records this scarcity in its chemistry. The Ogasawara Trench also sits within a specific oceanographic context that shapes the water chemistry around it. The Western Pacific in this region is influenced by the Kuroshio Current, the powerful, warm current that flows northward along Japan's eastern coast, analogous in some ways to the Gulf Stream in the Atlantic. The Kuroshio influences surface productivity in the region, and surface productivity ultimately determines how much organic material sinks toward the deep. The waters directly above the southern parts of the trench, away from the Kuroshio's influence, tend to be less productive, what oceanographers call oligotrophic, meaning nutrient poor. The northern parts of the trench, closer to the more productive waters around the Azu Islands and the Japanese coast, receive somewhat more organic input from above. This north-south gradient in food supply is real, and it likely shapes the distribution and abundance of Hadal life within the trench itself, though the sampling coverage to confirm this in detail is extremely limited. One thing worth saying clearly is that the Ogasawara Trench, in terms of the extremity of its conditions, is not simply comparable to the Mariana Trench, and left at that. The two systems are related. They are part of the same broader convergent margin, but they are not identical. The Mariana Trench is deeper at its maximum point, and the Challenger Deep at around 10,935 meters represents the deepest known point in the ocean. But the flanks of the Mariana Trench, at depths of 7,000 or 8,000 meters, are in some respects less extreme than the deepest parts of the Ogasawara Trench, which reaches close to 9,800 meters. A creature living at 9,000 meters in the Ogasawara Trench is experiencing pressures comparable to those at similar depths in the Mariana system, but the chemical and biological environment around them may be quite different. Different sediment composition, different organic carbon flux, different proximity to the volcanic arc, different current patterns above. These differences matter for biology. They are part of why researchers who study Hadal ecology do not treat all deep trenches as interchangeable. Each trench has its own character, and the organisms that live in it have adapted to that specific character, not just to depth in the abstract. There is also the matter of the trench's position relative to the volcanic arc above it. The Izubonin Islands and their associated submarine volcanoes sit on the Philippine Sea Plate, west of the trench. Hydrothermal activity associated with the arc, not within the trench itself but in the broader region, introduces chemical compounds into the water column that eventually influence the chemistry of the deep. Hydrogen sulfide, methane, and other reduced compounds associated with hydrothermal venting can, in principle, support chemosynthetic life, organisms that derive energy from chemical reactions rather than from sunlight. Whether chemosynthetic communities exist within the Ogasawara Trench itself has not been confirmed, but the geological conditions that would allow for them, serpentinization of ultramafic rocks along the trench walls, fluid seepage associated with the subducting plate, are present. It is a possibility that researchers have noted and that future surveys might investigate more directly. Taken together, what you have at the bottom of the Ogasawara Trench is an environment defined by extremes that compound one another. The pressure alone would be fatal to virtually every organism on Earth's surface. The cold slows every biological process. The darkness removes the energy source that drives almost all surface ecosystems. The food supply is sparse and irregular. The sediment is soft and chemically complex. And all of this sits within a geological structure that is actively moving, periodically shaken by earthquakes, and shaped by forces that operate on timescales of millions of years. It is, by any reasonable measure, one of the most hostile environments on the planet for life as we typically imagine it. Which makes the next question both obvious and genuinely fascinating, because something does live there. Several somethings, in fact, and some of them have been seen, and some of them have been collected, and some of them remain only glimpsed at the edges of camera frames or inferred from the logic of deep-sea biology. What the trench contains, and what it might still be hiding, is where this story gets considerably more interesting. So let us start with what science has actually confirmed. The Hadal Zone, that portion of the ocean below 6,000 metres, was once assumed to be essentially lifeless. The logic seemed sound at the time. The pressure was too extreme, the cold too persistent, the food too scarce. Early oceanographers in the 19th and early 20th centuries debated seriously whether anything could survive at those depths at all. The question felt almost philosophical. Then the dredges came back with things in them, and the debate shifted from whether life existed in the deep to what kind of life, and how much of it, and by what mechanisms it managed to be there at all. The organisms that dominate the Hadal Zone, the ones that show up consistently in traps and cameras and sediment cores from deep trenches around the world, are not the dramatic creatures that people tend to imagine when they think about the deep sea. There are no sea monsters in the conventional sense. What there is, in abundance, is something considerably smaller, and in its own way more remarkable. Amphipods are crustaceans, distantly related to the shrimp you might find in a supermarket, though they look rather different, laterally compressed, with curved bodies, multiple pairs of legs, and a kind of efficient, almost mechanical quality to their movement. They range in size from a few millimetres to, in the deep sea, something considerably larger. Hirondalia gigas, one of the most studied Hadal amphipod species, reaches lengths of around 3 centimetres and has been found in multiple deep trenches across the Pacific, including the Mariana, the Kermadec, and the Izubonin system. At Hadal depths, amphipods are frequently the most abundant macrofauna, the most numerous animals large enough to be seen with the naked eye. When a baited camera lander reaches the trench floor and the bait is deployed, amphipods often arrive within minutes, sometimes in swarms of hundreds or thousands, covering the bait in a dense churning mass. The speed of their arrival is one of the things that surprises people who see the footage for the first time. The trench floor looks empty and still, and then suddenly it is not. What makes amphipods particularly interesting in the context of the Ogasawara Trench is that they are not all the same. The amphipods found in different trenches are genetically distinct populations, and in some cases distinct species, shaped by the isolation of their respective environments. Samples recovered from the Izubonin region during Jamstek expeditions, particularly the surveys conducted in 2008 and again in 2011, which deployed freefall lander systems equipped with baited traps and cameras, showed amphipod assemblages that were consistent with Hirondalia gigas and related species. But the genetic analysis of these samples has contributed to a broader picture of how trench populations diverge from one another over time. The Ogasawara specimens are not simply identical to their Mariana cousins. They carry their own evolutionary history, shaped by the specific conditions of this specific trench. Beyond amphipods, the confirmed biology of the Hadal Zone includes polycate worms, bristle worms essentially, some of them predatory, some of them deposit feeders working through the sediment, which have been found at depths exceeding 9,000 meters in various Pacific trenches. Holothurians, the sea cucumbers, are another consistent presence. They move slowly across the sediment surface, processing large volumes of it through their digestive systems to extract organic material, and they have been observed at Hadal depths in multiple trench systems. Some of the Holothurian footage from deep landers is quietly striking. These pale, elongated animals moving in slow motion across a featureless plain of sediment, in complete darkness, at pressures that would destroy any human-built vessel not specifically engineered to withstand them. Foraminifera, single-celled organisms that build shells of calcium carbonate or agglutinated sediment particles, are present throughout the Hadal zone and contribute significantly to the sediment itself. Some foraminifera found at Hadal depths are giants by the standards of their kind, reaching several centimetres in size, a phenomenon associated with the deep sea's particular conditions. Their shells accumulate in the sediment over millions of years, and their chemistry records the history of the water column above them: temperature, chemistry, productivity, making them valuable not just as living organisms but as archives. Then there are the fish. The discovery that fish can survive at Hadal depths was, for a long time, considered unlikely. The physical constraints seem prohibitive. Fish rely on proteins that function within certain pressure ranges, and at extreme depths, those proteins are disrupted in ways that should, in theory, prevent normal biological function. What researchers found over decades of work was that Hadal fish have solved this problem through a specific biochemical adaptation involving a compound called trimethylamine oxide, or TMAO, which stabilizes proteins under pressure. The deeper the fish, the higher the concentration of TMAO in its tissues. This adaptation has a limit. The physics of TMAO concentration in cells suggest that fish cannot survive below approximately 8,200 meters, because the TMAO required to counteract the pressure at greater depths would itself disrupt cellular function. This theoretical limit has become known informally as the fish depth barrier, and it is supported by the observational record. No fish has been confirmed alive below around 8,300 meters, though the question remains open and actively debated. The deepest confirmed fish observation as of the time of writing is of Pseudoliparus swirae, a snailfish species, recorded at 8,178 meters in the Mariana Trench. Snailfish, members of the family Liparidae, have turned out to be the dominant vertebrates of the Hadal zone. They are not what most people picture when they imagine a deep-sea fish. They are small, pale, almost translucent, with soft bodies and no scales, and they look somewhat like tadpoles with fins. They are not dramatic in appearance, but they are extraordinarily well adapted to their environment, and they have been found in multiple deep trenches across the Pacific. The question of whether a distinct snailfish species inhabits the Ogasawara Trench is one that researchers have raised but not yet fully answered. The trench reaches depths where snailfish could plausibly survive. Its Hadal zone extends from around 6,000 meters down to nearly 9,800 meters, and the depth range between 6,000 and 8,200 meters is, in theory, accessible to snailfish biology. Jamstek lander deployments in the Izubonin region have captured footage that includes elongated fish at depth, and while some of these observations are consistent with known snailfish species from adjacent trench systems, others have not been immediately identifiable from the footage alone. Deep-sea taxonomy is difficult work under the best of circumstances. Identifying an organism from a few seconds of camera footage at 8,000 meters in low light with a fish that may be moving quickly or partially obscured is genuinely challenging. Some of what the cameras have captured near the Ogasawara Trench has been described by researchers as requiring further investigation, a careful phrase that, in the context of Hadal biology, means that what was seen did not clearly match any formally described species. This matters because of a broader pattern in deep-sea biology. Species found in Hadal trenches tend to be endemic, meaning they are found in that trench and nowhere else. This is not universally true. Some species, like Hirondelia gigas, appear across multiple trenches. But genetic studies have consistently shown that populations in different trenches are diverging from one another, and in many cases what looks like the same species across different trenches turns out, on closer examination, to be multiple distinct species that happen to look similar. The discovery of Pseudoliparus belyaevi in the Mariana Trench in 2019, a snailfish species formerly described from specimens collected there, is a useful example of how this works in practice. Before its formal description, it was simply footage of a pale fish at depth. After careful collection, preservation, and taxonomic analysis, it became a new species, distinct from the snailfish found in other trenches. The Ogasawara Trench, given its geographic separation from the Mariana and Kermadec systems, and the limited sampling that has been done there, is a plausible candidate for harbouring its own undescribed snailfish species. Whether that species has already been glimpsed in existing footage, or whether it has never been captured on camera at all, is genuinely unknown. The 2008 Jamstek expedition that targeted the Izubonin region used the Kairai research vessel and deployed freefall lander systems, essentially weighted frames carrying cameras, lights, bait, and collection traps, dropped from the surface and allowed to sink freely to the trench floor. Once on the bottom, they record footage and capture organisms attracted to the bait, then release their ballast weights and float back to the surface for recovery. It is a clever system, and it works reasonably well for sampling the mobile scavengers and predators that come to bait: amphipods, fish, occasional polychaetes. The 2011 deployments, conducted in the aftermath of the Tohoku earthquake, and as part of broader Pacific Survey work, added additional data points from the Izubonin Arc region, recovering amphipod samples from around 7,000 to 8,000 metres depth. What these expeditions confirmed was that the biological community in the Ogasawara Trench is real and active. Organisms are present, they respond to food sources, they are distributed across the depth range of the Hadal zone. What the expeditions could not confirm was the full picture of what is there, because the sampling footprint was tiny relative to the trench's actual size. Getting biological samples from 9,000 metres is not straightforward. The pressure alone presents engineering challenges. Collection traps that work reliably at 6,000 metres may fail at 9,000. Biological specimens recovered from extreme depths often suffer from decompression damage during ascent. The rapid pressure change as the lander rises through the water column can rupture cells, destroy delicate tissues, and make taxonomic analysis difficult or impossible. Preserving specimens chemically before or during ascent helps, but it introduces its own complications. Some organisms simply cannot survive the collection process in a condition that allows meaningful study. Sediment samples recovered from Hadal depths sometimes contain microbial communities and meiofauna, organisms too small to see without magnification, that are extraordinarily fragile and require specialised handling to study. The practical difficulties of deep Hadal biology are not trivial, and they explain why, despite decades of interest in these environments, the confirmed species list for any given trench remains short relative to what almost certainly exists there. There is also the matter of what the cameras have not captured, which is most of the trench. A lander system sitting on the seafloor illuminates a small circle of visibility, typically a few metres in diameter, for a period of hours. The Ogasawara Trench's Hadal floor below 6,000 metres covers thousands of square kilometres. The total area of seafloor directly observed by camera during all expeditions to this trench combined is, by any reasonable estimate, a vanishingly small fraction of the whole. Organisms that do not come to bait, sediment dwellers, slow-moving in fauna, organisms that avoid light or disturbance, are essentially invisible to lander-based surveys. The trench could contain dozens of species that have never appeared in front of a camera, simply because the camera has never been in the right place at the right time, or because the organisms in question have no reason to approach bait. What the available evidence does suggest, taken as a whole, is that the Ogasawara Trench supports a hadal biological community that is real, diverse by the standards of extreme environments, and incompletely known. The organisms that have been confirmed, amphipods, holothurians, polychaetes, foraminifera, and likely snailfish, represent a community shaped by the specific conditions of this trench, its pressure regime, its temperature, its sediment chemistry, its organic carbon flux, its geological activity. They are not random survivors. They are the result of millions of years of adaptation to this specific place, and the trench's relative isolation from adjacent systems means that some portion of what lives there almost certainly exists nowhere else on Earth. That portion, the organisms that are endemic to this trench, that have never been formally described, that may have been glimpsed in a few frames of lander footage or may not have been seen at all, is what makes the Ogasawara Trench genuinely interesting to researchers who study hadal biology, not as a mystery in the dramatic sense, but as a straightforward scientific gap. The trench is large, the sampling is minimal, the biology of comparable systems suggests endemism is likely. The conclusion that follows from those three facts is not sensational. It is simply that there are almost certainly organisms in the Ogasawara Trench that science has not yet named, described, or photographed. What makes this more than an abstract point is the scale of the gap between what has been sampled and what exists, and that gap, it turns out, is considerably larger than most people realise. To understand just how large that gap really is, it helps to sit with some numbers for a moment. Not as a list, but as a kind of slow reckoning with what they actually mean. The Hadal Zone, defined as ocean depth below 6,000 metres, covers roughly 37,000 square kilometres of seafloor globally, spread across the world's major trenches. The Ogasawara Trench alone accounts for somewhere in the region of 9,500 square kilometres of that Hadal seafloor. That is an area roughly comparable to the island of Cyprus, or the state of Delaware, sitting at the bottom of the Western Pacific at depth that no human being has ever physically entered. Across all Hadal zones on Earth, the total area of seafloor that has been directly sampled or observed, by camera, by physical collection, by any instrument that actually made contact with the bottom, is estimated at less than 0.0001% of the global seafloor. Not Hadal seafloor specifically, all seafloor. The Hadal zones are proportionally even less explored than that number suggests. That figure is worth pausing on. Less than 0.0001%, which means that if you were to take the entire floor of the world's oceans and lay it flat, the portion that science has actually seen up close would be smaller than a rounding error. And the Ogasawara Trench, which is not one of the most studied trenches even within that already tiny sample, has received a fraction of that already fractional attention. Part of why this is the case comes down to geography. The trench sits in the Western Pacific, in a corridor of ocean that is among the most typhoon-prone regions on Earth. Typhoon season in the Northwest Pacific runs roughly from May through November, which effectively limits the operational window for deep-sea research vessels to a few months of the year. Even within those months, weather windows for deploying sensitive equipment to 9,000 metres are narrow. A lander system dropped from the surface takes several hours just to reach the trench floor. The recovery operation takes additional hours. If conditions deteriorate during that window, and in the Western Pacific they can deteriorate quickly, the equipment may be lost entirely. This is not a hypothetical concern, it has happened. Jamstek's Kaiko ROV is probably the most significant single loss in the history of Hadal exploration. The Kaiko was not an ordinary remotely operated vehicle. It was built specifically for full ocean depth work, capable of reaching the deepest point of the Mariana Trench, and it had done exactly that in 1995, becoming only the third vehicle in history to reach Challenger Deep. It was an extraordinary piece of engineering, a two-body system with a primary vehicle and a smaller relay vehicle connected by a secondary cable designed to handle the enormous water column pressure across its tether length. The Kaiko had conducted surveys across multiple Pacific trenches, including work in the Izubonin region, and it represented years of investment and irreplaceable operational capability. In May 2003, while operating in the Western Pacific during a post-deployment recovery, a typhoon arrived faster than expected. The conditions overwhelmed the ship's ability to safely manage the vehicle, and the tether connecting the Kaiko to its launcher snapped. The ROV sank. It was never recovered. Jamstek lost in a single afternoon of bad weather, the only vehicle Japan had that could reach the deepest parts of the trench system it was most positioned to study. The replacement, a new vehicle called Kaiko Mark IV, was not completed until 2008, leaving a 5-year gap in Japan's full-depth operational capability. And even the replacement came with constraints. Deep ocean ROV programs are expensive to operate, expensive to maintain, and expensive to insure against exactly the kind of loss that claimed the original Kaiko. Research institutions do not send these vehicles out casually. Every deployment is planned carefully, budgeted carefully, and evaluated against the risk of losing equipment worth tens of millions of dollars. The Western Pacific Typhoon Corridor makes that risk calculation harder than it would be in calmer waters. Then there is the question of what the available vehicles can actually reach. Jamstek's Shinkai 6500 is one of the most capable human-occupied submersibles currently in operation anywhere in the world. It has conducted hundreds of dives across the Pacific and Indian Oceans, contributed to an enormous body of deep-sea research, and carried scientists to depths that would have seemed impossible a generation ago. Its operational depth limit is 6,500 meters. That number's right there in the name. And the deepest point of the Ogasawara Trench sits at approximately 9,780 meters, which means the Shinkai 6500, for all its capability, cannot reach the bottom third of the trench it is geographically closest to. The deepest and least understood portion of the Ogasawara Trench is simply beyond the reach of Japan's primary crewed research submersible. Scientists can get to 6,500 meters. They cannot get to 9,000. That gap, 2,500 meters of water, is not a small thing. It represents a pressure increase of roughly 250 additional atmospheres, and it contains an entirely different biological environment from what the Shinkai can access. The vehicles that can reach full Hadal depth, the kinds of systems that went to Challenger Deep, are few, expensive, and not dedicated to the Ogasawara Trench specifically. The DSV limiting factor, operated by Inkfish and previously by Caladan Oceanic, reached Challenger Deep multiple times between 2019 and 2022 and has demonstrated that full ocean depth crewed dives are operationally feasible. But it is a single vehicle, and the Pacific has dozens of major trenches. Deploying it to the Ogasawara Trench for a sustained survey program would require funding, ship time, logistical coordination, and a scientific justification strong enough to compete with every other deep ocean priority on the list. None of that is impossible. It simply has not happened yet. Freefall lander systems, the unmanned baited camera platforms that Jamstek and other institutions have used in the trench, are considerably more affordable than crewed or tethered ROV systems. A single lander deployment, depending on the equipment configuration and the ship time involved, can cost somewhere in the range of tens of thousands to several $100,000 when all operational costs are included. That sounds like a lot, and it is, but it is modest compared to the cost of a full crewed submersible program. Landers have the advantage of simplicity. They sink, they record, they float back up. There are no pilots, no life support systems, no tether management. They can be deployed from a wider range of vessels, and they can reach depth that crewed systems cannot. The 2016 Ogasawara survey that recovered amphipod samples from around 8,500 meters used exactly this kind of system, and it worked. But landers have their own limitations. They cover a small area. They depend on organisms coming to them. They cannot navigate, cannot follow a feature of interest, cannot collect a sediment core or scrape a rock sample from a trench wall. They are a window into a small circle of seafloor, open for a few hours and then gone. Acoustic mapping has covered considerably more ground than any physical sampling. Multi-beam sonar systems mounted on research vessels can map the seafloor topography across wide swaths without needing to descend to depth. JAMSTEC and other institutions have produced bathymetric maps of the Ogasawara Trench that show its general shape: the long, narrow valley, the asymmetric walls, the sediment accumulations in the deepest axis, the scarps and ridges that mark the subduction boundary. These maps are genuinely useful. They tell you where the deep water is, where the sediment has piled up, where the walls are steep. They do not tell you anything about what lives there. Sonar sees the shape of the seafloor. It does not see the organisms on or within it. A multi-beam survey can map thousands of square kilometres in a single cruise, but the biological picture it produces is essentially blank. You know the terrain, you do not know the inhabitants. Sediment cores add another layer of information. Cores recovered from Hadal depths contain microbial communities, chemical signatures, records of past sedimentation events, and sometimes preserved biological material from organisms that lived and died in the trench over geological time. They're invaluable for understanding the trench's history and its current chemical environment. But coring is also a slow, technically demanding process, and the cores recovered from the Ogasawara Trench represent a handful of data points scattered across a very large area. The sediment record is real and informative. It is also radically incomplete. What all of this adds up to is a situation that is, in its own quiet way, somewhat humbling. The Ogasawara Trench has been known to exist for decades. It has been mapped, visited, sampled, and studied by some of the most capable deep-sea research institutions in the world. Japan, which sits directly above this trench, has invested more in Hadal research than almost any other nation. And yet the actual scientific coverage of the trench, the area of its floor that has been observed, the fraction of its biology that has been catalogued, the portion of its chemical environment that has been measured, is genuinely tiny. Not because of lack of interest or lack of effort, but because the trench is deep, the Western Pacific is hostile, the tools that can reach the deepest parts are rare and expensive, and the ocean does not make any of this easy. There is also something worth noting about the way scientific attention distributes itself. The Mariana Trench gets more coverage, in research, in media, in public imagination, partly because Challenger Deep is the deepest point on Earth, and that superlative carries weight. The Kermadec Trench in the southwestern Pacific has received significant attention from New Zealand-based researchers and from Alan Jameson's group at Newcastle, who have done extensive lander work there. The Japan Trench, which runs along the northeastern coast of Japan and was the site of the 2011 Tohoku earthquake seafloor rupture, has received considerable study because of its direct relevance to Japanese earthquake and tsunami risk. The Ogasawara Trench sits in a slightly different category: significant, deep, geologically active and biologically interesting, but without a single dramatic superlative to anchor public or institutional attention. It is not the deepest. It is not the most earthquake-prone. It is not the closest to a major city, though it is not far from Tokyo. It is simply one of the deeper and less studied trenches in the Pacific, which means it has received correspondingly less of the limited resources available for Hadal research. That relative neglect is not a criticism of anyone. It is just how scientific attention works in a world where resources are finite and priorities have to be set. But it does mean that the Ogasawara Trench is, by any reasonable measure, one of the least understood major Hadal environments on Earth. The sampling that has been done confirms that a biological community exists there. The size of the sampling relative to the size of the trench means that the community is almost entirely uncharacterized. The geographic isolation of the trench from adjacent systems means that endemism is likely. The combination of those facts points in one clear direction. There are things living in the Ogasawara Trench that science does not yet know about. Not as speculation, not as wishful thinking, but as a straightforward consequence of the numbers involved. And so the question that naturally follows is not whether undiscovered life exists in the trench. That much seems almost certain by the logic of what comparable systems have yielded and how little of this one has been examined. The question is how scientists have actually tried to work around the limitations, how they have made the most of the tools available, and what the specific expeditions to this trench have managed to see and recover despite all of those constraints. Because the picture that has emerged from the Ogasawara Trench, incomplete as it is not empty. The cameras have been there, the landers have descended, and what they have recorded across a small but real collection of dives and deployments turns out to be more interesting than the bare species lists might suggest. So let us talk about what has actually happened out there, the specific work, the ships that went, the instruments that descended, the footage that came back. JAMSTEC, the Japan Agency for Marine Earth Science and Technology, has been operating in the Izu-Bonin region since the early 1990s, and their survey history in these waters is longer and more detailed than most people realise. The agency was established in 1971, originally under a different name, and deep sea research became one of its central missions in the decades that followed. The Ogasawara Trench sits, in a sense, in JAMSTEC's backyard. It runs south from waters just off the Japanese coast, and Japan's scientific interest in the subduction zone beneath it, for earthquake monitoring, for geological understanding, for basic oceanographic research, has kept research vessels returning to this region across multiple decades. The work has not always been specifically biological. A great deal of it has been geological, seismological, physical oceanographic. But the cumulative presence of Japanese research vessels in these waters has produced a body of survey data that, while incomplete, is more substantial than the trench's relative obscurity might suggest. The research vessel Kairai is one of the ships most associated with deep water work in this region. Commissioned in 1997, the Kairai was designed specifically for deep-sea research and has been deployed repeatedly in the Western Pacific, including in the Izu-Bonin area. At roughly 100 meters in length and equipped with multi-beam sonar, sediment coring systems and deployment infrastructure for ROVs and freefall landers, the Kairai is the kind of ship that can do multiple types of science in a single cruise, mapping one day, coring the next, deploying a lander the day after. It is a capable vessel, and its cruises to the Ogasawara region have contributed meaningfully to what is known about the trench's physical structure and, to a lesser extent, its biology. The freefall lander is worth describing in some detail, because it is the instrument that has done most of the biological work in the trench, and it is a stranger piece of technology than the name suggests. A lander, in this context, is essentially a weighted frame, usually made of aluminium or titanium since both materials handle pressure well, fitted with cameras, light sources, bait containers and collection traps. It has no tether connecting it to the surface. You drop it over the side of the ship and it sinks. It takes several hours to reach Hadal depths. The cameras run on battery power. The bait, typically mackerel or a paste made from fish meal, is attached to the frame or placed inside a mesh container, and it begins releasing scent into the water column as the lander descends. By the time the frame reaches the seafloor and settles into the sediment, the bait plume has been drifting upward and outward for hours, and whatever lives in the surrounding trench has had time to detect it. After a programmed interval, which might be 12 hours or 24 or longer depending on the mission design, a release mechanism fires. This is usually an acoustic command sent from the ship, or sometimes a simple timer. The mechanism drops the ballast weights that held the lander on the bottom, and the frame, now positively buoyant because of its syntactic foam floats, rises back toward the surface. The whole round trip from deployment to recovery can take the better part of a day, And when the lander comes back up, if everything has worked, if the battery held, if the cameras did not flood, if the release fired, if the current did not carry it too far for the ship to find, you have footage. You have trap contents. You have a small, imperfect but real window into what was happening 9 kilometers below the surface of the Pacific. In the 2016 survey of the Ogasawara Trench, landers deployed from a Jamstek vessel recovered amphipod samples from approximately 8,500 meters depth. This was not the first time amphipods had been recovered from this trench system, but the 2016 samples contributed to a growing dataset about the crustacean communities at Hadal depths in the Izubonin Arc. The amphipods recovered were large by crustacean standards. Some specimens of Hirondelia gigas and related species reached several centimetres in length, and they arrived at the bait in numbers. The trap contents from a single deployment can include hundreds of individuals. This is not unusual for Hadal amphipod communities. They're efficient scavengers, highly adapted to detecting and exploiting food sources in an environment where meals are rare and unpredictable. When food appears, they respond quickly and in force. The camera footage from these deployments is, in a sense, the most viscerally informative thing to come out of Hadal lander work. You see the seafloor in the light of the lander's LEDs, pale sediment, flat and featureless except for the occasional burrow or trail, extending to the edge of the light and then disappearing into absolute darkness. For a while, nothing happens. Then the amphipods arrive. They come in from the edges of the frame, small pale shapes moving with surprising speed across the sediment. Within minutes of the first arrivals, there can be dozens. Within an hour, the bait is often covered. The footage from the Ogasawara landers shows this same pattern. The empty seafloor, the gradual accumulation, the feeding swarm. It is both mundane and quietly astonishing, because you're watching creatures that live their entire lives in a place that is, by almost any human measure, incompatible with life. Interspersed with the amphipod footage, the cameras have occasionally recorded other organisms. Holothurians, sea cucumbers, appear in some of the lander footage from the Izubonin region. They move slowly across the sediment, ingesting it as they go, extracting whatever organic material it contains. They are not there for the bait specifically, they are simply doing what holothurians do, which is to move through the sediment in a slow, methodical way that looks, from a distance, almost meditative. At Hadal depths, some holothurian species are surprisingly abundant. In certain trenches, they make up a significant fraction of the visible megafauna. In the Ogasawara lander footage, they appear less frequently than the amphipods, but their presence is noted and documented. The acoustic mapping that has been done over the Ogasawara Trench gives a detailed picture of the seafloor's shape, and that shape is more varied than a simple description of a long, narrow valley might suggest. The trench axis, the deepest part, runs roughly north to south, but it is not a smooth channel. There are sections where the floor widens, where sediment has accumulated in thick deposits, where the walls are relatively gentle slopes, and other sections where the scarps are steep and the relief is dramatic. The deepest recorded point in the trench, at around 9,780 meters, sits in the southern portion of the system, closer to where the Ogasawara Arc begins to merge with the broader Mariana system. The northern portions of the trench are somewhat shallower, and the character of the seafloor changes along the trench's length. More sediment accumulation in some areas, more exposed rock in others, different wall geometries depending on the local structure of the subduction boundary. This topographic variation matters for biology, though in ways that are not yet fully understood in this specific trench. In other Hadal systems, researchers have found that the deepest axis of a trench tends to accumulate both sediment and organic material, funneled down from the walls and from turbidity currents. The organisms that live in the axis may experience different food availability than those living on the walls at shallower Hadal depths. The walls themselves can host different communities than the flat axis floor. Whether similar patterns hold in the Ogasawara Trench is an open question. because the biological sampling has not been systematic enough across the trench's depth range to answer it. But the sonar data at least establishes that the physical environment is heterogeneous, which is a reasonable basis for expecting biological heterogeneity as well. Sediment cores from the trench have provided a different kind of information. The sediment in the deepest parts of the Ogasawara Trench is composed largely of fine clay and biogenic ooze, the accumulated remains of microscopic organisms that lived in the surface waters above and sank over millions of years. Within this sediment, microbial communities exist at densities that are lower than in shallower marine sediments, but still represent a significant biomass. The cores have also captured chemical signatures, oxygen profiles, organic carbon content, isotopic ratios, that tell researchers something about the current and historical conditions in the trench. Some cores show evidence of episodic sedimentation events, layers where material was deposited rapidly rather than gradually, which is consistent with turbidity currents triggered by earthquakes. The sediment record, in other words, contains a geological history of the trench's dynamics, including the periodic disturbances that reshape its floor. What the cameras have caught, beyond the amphipod swarms and the occasional holothurian, is where things become harder to categorize neatly. In lander footage from the broader Izu-Bonin region, and here it is worth being precise because the footage comes from different deployments at different depths and locations across the arc, there have been observations of elongated pale fish moving at the edges of the camera frame. These are not always well lit, not always close enough to the camera for clear identification, and not always present long enough for confident species assignment. In some cases, the fish observed have been tentatively associated with snailfish, members of the family Liparidae, which are the dominant vertebrate predators in hadal environments globally. But in other cases, the identification has been less certain. The fish observed in some Izu-Bonin lander footage did not match cleanly with known species from adjacent trenches, which raises the possibility, not a confirmed finding but a reasonable scientific possibility, that the trench hosts its own distinct fish fauna. This is not a dramatic claim. It is, in fact, a fairly routine observation in hadal biology that different trenches tend to have different species, even within the same genus. But it does mean that the footage from the Izu Ogasawara landers contains organisms that have not been fully accounted for in the scientific literature. Some of what the cameras have seen has not been described. That is simply the state of knowledge in this system. Not a mystery in the sensational sense, but a genuine scientific gap. The organisms were there, the cameras recorded them, the footage exists, and the work of identifying, classifying and formally describing what was observed is ongoing, slow and constrained by the same resource limitations that constrain every other aspect of hadal research. There is something worth sitting with in that image. A camera sitting on the seafloor at 8,500 meters, running on battery power in complete darkness except for its own lights, recording creatures that may not have a scientific name. The footage comes back to the surface, gets reviewed by researchers, gets compared to known species, and sometimes the comparison does not resolve cleanly. The organism in the footage is real. It was there. It moved through the frame and disappeared back into the dark. And the question of what it was remains for the moment unanswered. The lander work in the Izu Ogasawara Trench has produced this kind of result more than once. Not dramatic footage of enormous unknown creatures. That is not what hadal landers typically capture, and it would be misleading to suggest otherwise. What the cameras have produced is something more modest and, in its own way, more genuinely interesting. A record of organisms that are real, present, and not yet fully understood. Pale fish at the edge of the light, holothurians moving in patterns that surprised the researchers watching the footage, amphipods that, on closer examination, did not match exactly the populations described from other trenches. Small details, each one individually easy to set aside but collectively pointing toward a biological community that is distinct and incompletely characterized. The cameras have been there. That is the thing to hold on to. The Ogasawara Trench is not entirely unobserved. It is observed, but observed through a keyhole, a small circle of light on a vast dark floor, open for a few hours at a time, in a handful of locations across a system that stretches for nearly 1,000 kilometers. What falls within that circle of light is documented. What lies beyond it in the darkness that the cameras cannot reach is still unknown. And it is in that darkness, in the unsampled sections of the trench, the unvisited depths, the areas of the wall and floor that no lander has ever settled near, where the more interesting questions begin to take shape. Because if the small fraction of the trench that has been observed already contains organisms that are difficult to identify, the logical implication of that is not reassuring for anyone who prefers a complete picture. It suggests that the complete picture is very far from being assembled. And the next question, the one that follows naturally from everything the expeditions have found and failed to find, is what those unidentified organisms actually are, and whether the trench, by virtue of its isolation and its depth, has been producing life that exists nowhere else on Earth. That question, whether the trench has been producing life that exists nowhere else on Earth, is not a speculative one, at least not in the way that phrase usually sounds. It is grounded in a pattern that Hadal biologists have been documenting for decades, and the more carefully you look at the evidence, the more that pattern becomes difficult to dismiss. The Ogasawara Trench, based on what little has been observed there, appears to follow that pattern. And understanding why requires spending some time with the specific organisms that have been glimpsed in lander footage from the region. Not the dramatic unknowns, but the ones that sit in that uncomfortable middle category, seen, recorded, compared to known species and not quite resolved. The elongated, pale fish that have appeared at the edges of Izubonin lander footage are the clearest example of this. When researchers review Hadal lander footage, the first step in identifying a fish is to compare its morphology, body shape, fin placement, coloration, size, against the catalogue of known Hadal species. For snailfish, the family Liparidae, that catalogue has grown considerably in the last decade. The discovery of Pseudoliparis swirri in the Mariana Trench, formally described in 2017 after footage and specimens were collected at depths reaching 8,178 metres, gave researchers a much clearer picture of what a Hadal snailfish looks like at extreme depth. Translucent, elongated, with a broad head, small eyes, and a characteristic tadpole-like body. That description became a reference point. When similar fish appeared in footage from other trenches, the comparison began there. What made some of the Izubonin footage harder to categorise was not that the fish looked dramatically different. It was that the differences were real, but subtle. Proportions that did not quite match, coloration that was slightly off, behaviour at the bait that did not align neatly with what Mariana snailfish populations had been observed doing. These are not the kinds of differences that make headlines. They are the kinds of differences that make a researcher pause, re-watch the footage several times, pull up the comparison images, and write a note in the margin of their field log that says something like, "Not immediately assignable to known species." That note does not mean the creature is unknown to science in a dramatic sense. It means the identification is uncertain, and that uncertainty is itself significant. Because in a system as poorly sampled as the Ogasawara Trench, uncertain identifications tend to resolve in one of two directions. Either the footage eventually gets matched to an existing species as better reference material becomes available, or it becomes the first evidence of something that was not previously described. The question of whether a distinct snailfish species exists in the Ogasawara Trench, separate from the populations documented in the Mariana or Japan trenches, is genuinely open. It has not been answered. There have been no specimens physically recovered from the deepest parts of the trench that would allow the genetic and morphological analysis needed to formally describe a new species. The footage alone is not enough for that, but the footage is enough to say that the fish observed in this trench do not appear to be straightforward representatives of already documented populations, and that the biological case for a distinct species here is plausible, supported by what is known about how Hadal fish populations behave across different trench systems. The holothurians, sea cucumbers, observed in some of the Izubonin lander deployments are a slightly different case. Holothurians are common in Hadal environments. They are in fact among the most abundant megafaunal organisms in the deepest parts of ocean trenches, and in some Hadal systems they dominate the visible fauna to a remarkable degree. In the Mariana Trench, certain holothurian species have been observed in densities that surprise researchers, moving slowly across the sediment, feeding on organic particles, seemingly indifferent to the cameras observing them. So finding holothurians in Izubonin footage was not surprising. What drew attention in some of the footage was the movement. Holothurians at depth tend to be slow, methodical creatures. Their locomotion is not dramatic. But in certain frames of Izubonin lander footage, researchers noted holothurians moving in ways that seemed more active than expected, changing direction, responding to the presence of the bait in ways that suggested a different behavioural profile than what had been documented in other trenches. Whether this reflects a genuinely distinct species, a behavioural variant of a known species, or simply the natural variation of individual animals under particular conditions is not clear. It is one of those observations that sits in the record, noted, not explained, waiting for more data. What makes all of this more than a collection of ambiguous footage is the broader biological framework that surrounds it. The concept of Hadal endemism, the tendency for trench species to be found only in one trench, or one small cluster of trenches, has become one of the central organising ideas in deep sea biology over the last 20 years, and the evidence for it is not speculative, it is genetic. Researchers studying amphipod populations across different Hadal trenches have found that populations separated by even a few thousand kilometres of abyssal plain are genetically distinct. The abyssal plain, which sits at roughly 4,000 to 5,000 metres depth, is not a barrier in the way a mountain range is a barrier. There is no physical wall. But for an organism adapted to pressures of 800 or 900 atmospheres, crossing a region where the pressure drops to 400 atmospheres is not straightforward. The physiology that makes life possible at 9,000 metres may make life difficult or impossible at 4,000 metres. The trench, in this sense, is not just a deep place, it is an island of extreme conditions surrounded by slightly less extreme conditions that still function as a boundary. This is not a new idea in biology. Island biogeography, the study of how isolation shapes species diversity and evolution, has been applied to oceanic islands, mountain peaks, isolated lakes, and cave systems for decades. The application to Hadal trenches is more recent, but the logic is the same. Isolated populations separated for long enough diverge. The longer the isolation and the more extreme the selection pressures, the more distinct the divergence tends to be. The Ogasawara Trench has been in roughly its current form for millions of years. The subduction zone that created it has been active for far longer. The populations of organisms living at its greatest depths have had an enormous amount of time to diverge from populations in adjacent trenches, and the genetic evidence from systems that have been studied more thoroughly, the Mariana, the Kermadec, the Japan Trench, consistently shows that this divergence is real. The 2019 formal description of Pseudoleparus belyaevi from the Mariana Trench is worth mentioning here, not because it directly involves the Izu-Ogasawara system, but because it illustrates how this process works in practice. Pseudoleparus belyaevi was described based on specimens and footage collected from the Mariana at depths between 7,000 and 8,200 metres. It is closely related to Pseudoleparus suirae, which was described 2 years earlier from the same trench. Two species, same genus, same trench, separated by depth rather than geography. each one representing a distinct evolutionary lineage that developed under slightly different conditions within the same system. If a single trench can contain multiple distinct species of snailfish at different depth ranges, then the question of whether the Ogasawara Trench contains its own distinct snailfish species, or multiple species, is not a long shot. It is, based on the pattern established in the Mariner, a reasonable expectation. The problem is that reasonable expectations in Hadal biology require extraordinary logistical effort to confirm. Describing a new species requires specimens, physical tissue that can be analysed genetically and morphologically. Getting specimens from 9,000 metres means deploying a trap system capable of functioning at that depth, recovering it successfully, and bringing back organisms in a condition that allows proper analysis. The Ogasawara Trench, sitting in the typhoon corridor of the Western Pacific, does not make this easy. Deployments have to be timed carefully. Equipment has to be robust enough to survive conditions that have, in the past, destroyed far more expensive instruments. And even when everything goes correctly, the trap may come back empty, or with specimens that did not survive the pressure transition during ascent, or with amphipods but no fish. The logistics impose their own uncertainty on top of the biological uncertainty. There is also the question of what the cameras have not captured at all. Not unidentified organisms, but simply the absence of observation in the vast majority of the trench. The lander deployments that have occurred in the Ogasawara system have been concentrated in a relatively small number of locations, mostly in the northern and central portions of the arc. The southern reaches of the trench, approaching the transition toward the Mariana system, have been sampled even more sparsely. The deepest point of the trench, around 9,780 metres, has not been directly surveyed with biological instruments. What lives at the very bottom of the Ogasawara Trench, in the sediment and in the water column immediately above it, is genuinely unknown. Not poorly characterised. Unknown. This is worth sitting with for a moment, because it is easy to read past it. The deepest point of a trench that stretches nearly 1,000 kilometres through one of the most geologically active regions on Earth has not been directly observed by any biological instrument. The sonar has mapped the shape of the floor there, the depth has been measured, but whether there are organisms living at that depth, what they are, how abundant they are, and how they relate to populations elsewhere in the trench, all of that is open. The cameras have not been there. The traps have not been there. The closest analogy in more familiar terms would be knowing the shape of a forest from aerial photographs, but never having walked into it, never having seen what lies under the canopy, never having collected a single specimen from the ground. What the Ogasawara footage and samples have collectively established is a partial picture, partial in a way that is not diminished by being partial, but that needs to be understood clearly. The trench contains amphipods that differ from populations in adjacent systems. It contains fish that do not match cleanly to known species. It contains holothurians that behave in ways that are not entirely consistent with what has been documented elsewhere. And it contains, in its deepest and least observed sections, a biological community that has had millions of years to develop in relative isolation. The combination of those facts does not prove the existence of undescribed species. It does something more straightforward than that. It makes the existence of undescribed species the most parsimonious explanation for what the data shows. In science, that is not proof, but it is the kind of inference that drives the next expedition, funds the next lander deployment, and motivates the next generation of researchers to spend years of their careers on a problem that most people have never heard of. The organisms glimpsed in the Izubonin footage, the pale fish at the edge of the light, the holothurians moving in unexpected ways, are not anomalies in the data. They are, in a sense, the data behaving exactly as the biological framework predicts it should. A trench this deep, this old, this isolated, and this poorly sampled should contain organisms that are difficult to identify, because identification requires comparison, and comparison requires a complete reference catalogue, and the reference catalogue for Hadal life is nowhere near complete. The Ogasawara Trench is contributing to the incompleteness of that catalogue, not by being unusual, but by being what every Hadal system appears to be when examined carefully: a distinct biological world shaped by its particular geography, its particular chemistry, and its particular history. And that history, the evolutionary history encoded in the organisms living there, connects directly to a deeper question about what makes the Ogasawara Trench different, not just from other trenches in general, but from other trenches in terms of the specific conditions that shape the life within it. Because the biology does not exist in isolation from the chemistry and the geology. The organisms that live in the trench are not simply adapted to depth in a generic sense. They are adapted to this trench, with its particular sediment composition, its particular temperature profile, its particular input of organic material from above, and its particular geological dynamics below. And those conditions, it turns out, are not identical to what you would find in the Mariana, or the Kermadec, or the Japan Trench. The Ogasawara Trench has its own chemical character, and that character shapes, in ways that are still being worked out, what can live here and how. To understand why the Ogasawara Trench might harbour life found nowhere else on Earth, it helps to think about what a trench actually is from a biological perspective, not geologically, not physically, but in terms of the organisms that live there. From that angle, a Hadal trench is less like a feature of the seafloor and more like an island. A very deep, very dark, very cold island, but an island in the functional sense that matters most to evolution. It is isolated. The populations living at the bottom of one trench cannot easily reach the bottom of another. The barriers between them are not walls of rock or stretches of open water that a swimming animal might cross. The barriers are pressure gradients and depth thresholds that the animals themselves cannot survive crossing. The abyssal plains that separate one trench system from another sit at roughly 4,000 to 5,000 metres depth. That sounds deep by any ordinary measure, and it is. But for an organism adapted to pressures above 800 atmospheres, the kind of pressure you encounter below 8,000 metres, those abyssal plains are not a neutral corridor. They are, in a physiological sense, shallow. The pressure at 4,000 metres is around 400 atmospheres. For a creature whose proteins and cell membranes have been tuned by millions of years of selection to function at pressures twice that high, moving upward into those conditions is not a minor inconvenience. It is a fundamental physiological challenge. Some species may be able to tolerate a range of pressures, but the deep specialists, the organisms that have committed fully to Hadal life, likely cannot make that crossing. And so each trench becomes, over geological time, its own contained experiment in evolution. This is the concept of Hadal endemism, and it is one of the most compelling ideas in deep-sea biology. The word endemic simply means found only in a specific place, not distributed widely, but confined to a particular region. Island species are often endemic. Cave species are often endemic. And Hadal species, it turns out, are frequently endemic to individual trenches. The Ogasawara Trench, the Mariana Trench, the Kermadec Trench south of New Zealand, the Tonga Trench, the Japan Trench running parallel to the Japanese coast. Each of these is not just a geographic feature. Each is, biologically speaking, a separate world. The person who has done perhaps more than anyone else to document and articulate this pattern is Alan Jameson, a deep-sea ecologist who spent many years at the University of Aberdeen and later at Newcastle University. Jameson has led or contributed to lander expeditions across multiple Hadal systems, and his work has been central to establishing how distinct these trench populations actually are. His 2015 book, simply titled The Hadal Zone, remains one of the most comprehensive treatments of this environment, not just describing what lives in Hadal trenches, but working through the ecological and evolutionary logic of why those communities look the way they do. Reading through his work, you get a clear sense of how much the field has advanced in a relatively short time, and also how much remains genuinely open. Jameson's genetic studies and related work by other researchers have found that amphipod populations in different trenches are not the same. Hirondellea gigas, one of the most commonly encountered hadal amphipods, shows genetic differentiation between populations from the Mariana, the Kermadec, and the Izubonin systems. These are not dramatically different species, at least not based on current classification, but the genetic distances between them reflect long periods of isolation. The populations have been separated long enough that their DNA has diverged in measurable ways. That divergence is the molecular fingerprint of geographic isolation operating over deep time. What this means practically is that the amphipods in the Ogasawara Trench are not simply the same animals that live in the Mariana, distributed across both systems because the two trenches happen to be in the same ocean basin. They are related, yes, but they are distinct. They have been shaped by the specific conditions of their specific trench, and they carry in their genomes the record of that separation. And if that is true for amphipods, which are relatively mobile, relatively robust, and relatively tolerant of a range of conditions, then it is likely even more true for organisms that are more specialized, more pressure-dependent and less capable of dispersal. The snailfish, the polychaete worms, the holothurians, the foraminifera in the sediment, all of these groups, in all likelihood, show the same pattern of trench-level endemism, possibly to an even stronger degree. The pressure adaptation question is particularly interesting here. Organisms that live at 8,000 meters or deeper have biochemical machinery that functions under conditions which would destroy the proteins of a surface animal. One of the key mechanisms involves a molecule called trimethylamine oxide, or TMAO, which acts as a pressure stabilizer for proteins. We will come back to this in more detail later, because it has some fascinating implications for the physical limits of vertebrate life. But the relevant point for endemism is this. The degree of pressure adaptation required to live at 9,000 meters is not something an organism can acquire quickly. It represents a deep evolutionary investment, and an organism that has made that investment is by definition committed to the hadal zone. It cannot retreat to shallower water. The very adaptations that make it capable of surviving at depth make it physiologically dependent on depth. It is locked in. This creates a kind of evolutionary ratchet. Once a lineage colonizes a hadal trench and begins adapting to the extreme pressure, it becomes progressively less capable of leaving. Each generation that is better adapted to the trench is also, in a sense, more confined to it. Over millions of years, this produces populations that are exquisitely suited to their particular trench and essentially unable to exist anywhere else. The Ogasawara Trench has been in roughly its current form for tens of millions of years. The subduction zone that created it is one of the older convergent margins in the Pacific. That is an enormous amount of time for this evolutionary ratchet to operate. The implication for undescribed species is straightforward. If the Ogasawara Trench has been isolated for tens of millions of years, and if the organisms living there have been progressively adapting to its specific conditions during that time, then the trench should contain species that exist nowhere else. Not variations on species found in adjacent trenches. Distinct species with their own morphology, their own genetics, their own ecological roles. The fact that the trench has been sampled so sparsely means that most of those species have not been collected, examined, named, or described. They are present in the biological sense, living, reproducing, dying in the dark at the bottom of a trench that most people have never heard of, but they are absent from the scientific record. They do not yet exist in any catalogue or database. They are real and they are unknown. The Mariana Trench provides the clearest recent model for what discovery in an isolated hadal system looks like. In 2019, researchers formally described Pseudoliparis belliaevi, a snailfish species found in the Mariana at depths exceeding 8,000 meters. This was not a species that had been hiding in plain sight. It was genuinely new to science, collected from a system that had been studied far more extensively than the Ogasawara Trench. If a new vertebrate species could be waiting in the Mariana, which has received more scientific attention than any other Hadal system, then the Ogasawara Trench, less studied, less visited, less sampled, almost certainly contains equivalents. Not necessarily snailfish, though that is possible, but organisms at a similar level of complexity, adapted to the specific conditions of this specific trench, that have not yet been formally encountered by science. There is something quietly remarkable about this. We tend to think of undiscovered species as belonging to remote tropical rainforests, or to unexplored cave systems, or to the deep Amazon. The idea that vertebrate animals, fish, with backbones and eyes and fins, might exist in a trench less than 2,000 kilometers from Tokyo, undescribed and unobserved, sits oddly against our assumptions about how well mapped the modern world is. The Ogasawara Trench is not in some impossibly remote corner of the planet. It is in the Western Pacific, in a region that has been fished, sailed, fought over, and studied for centuries, and yet its deepest reaches contain life that no human has seen. Jameson has written about this with a kind of careful patience that characterises the best deep-sea science. The Hadal Zone, he argues, should not be thought of as a single environment. It is a collection of distinct environments, each shaped by its own geology, its own chemistry, its own history of isolation, and its own evolutionary trajectory. Treating all Hadal trenches as variations on the same theme misses the point. Each trench is its own thing. The Ogasawara Trench is not a lesser version of the Mariana or a northern extension of the Kermadec. It is the Ogasawara Trench, with its own amphipod populations, its own fish, its own sediment chemistry, its own geological dynamics, and its own biological community that has been developing in isolation for longer than our species has existed. The sampling data, sparse as it is, already hints at this distinctiveness. The amphipods recovered from Bonin lander deployments are genetically differentiated from Mariana populations. The unidentified fish observed in lander footage do not match cleanly to species described from adjacent systems. The holothurians move differently, feed differently, appear in densities and configurations that do not quite fit the patterns documented elsewhere. None of this is proof of new species in the strict taxonomic sense, but it is consistent with the prediction that endemism makes, that a long-isolated, deeply adapted community will look different from its neighbours, because it has been on a different evolutionary path. What makes this particularly interesting is the question of how far that divergence extends. Endemism in amphipods is well established. Endemism in fish is suspected but not yet confirmed for the Ogasawara system specifically. But what about organisms further down the complexity scale? Polychaete worms, foraminifera, the microbial communities in the sediment. The deeper you go into the biological hierarchy, the less we know about trench-level endemism, and the more likely it becomes that the patterns are even more pronounced. Microbial communities in Hadal sediments are shaped by the local chemistry, the local temperature, the local input of organic material, and the local geological activity. Those conditions vary between trenches. The microbial life varies too. And in a trench like Ogasawara, where the chemistry has some distinctive features that we'll get to shortly, the microbial community may be as distinctive as anything living in the water column above it. The picture that emerges from all of this is of a trench that functions as a biological archive. Not a static one. The organisms living there are not fossils. They are alive and active and responding to their environment in real time. But an archive in the sense that the trench has preserved, through its isolation and its extreme conditions, a biological lineage that has been developing independently for an enormous span of time. Every organism in the Ogasawara Trench carries, in its body and its genome, information about how life adapts to extreme isolation and extreme pressure. that information is not duplicated anywhere else, because the evolutionary history that produced it happened here, in this trench, under these specific conditions. Losing access to it, through inadequate sampling, or through contamination, or simply through the passage of time before the next expedition arrives, would be a genuine scientific loss. Not a dramatic one, not the kind that makes headlines, but a quiet, irreversible narrowing of what we can understand about life on Earth. This is why the concept of Hadal endemism is not just an interesting theoretical framework. It's a practical argument for why the Ogasawara Trench deserves more attention than it has received. The biology is telling us something specific. This place contains life that exists nowhere else, shaped by conditions that exist nowhere else, carrying evolutionary information that cannot be recovered from any other location. The trench is not just deep, it is singular, and the chemistry that underlies that singularity, the particular mix of geological activity, sediment composition, and chemical gradients that defines the Ogasawara environment, turns out to be as distinctive as the biology it has produced. So let us talk about the chemistry, because the Ogasawara Trench is not just geologically active in a general sense. It sits within one of the oldest and most complex convergent margins on the planet, and that history has left a very specific chemical signature in the water, the rock, and the sediment at its deepest points. The Isobonin-Mariana convergent margin, of which this trench is the northern expression, has been an active subduction zone for somewhere between 50 and 60 million years. That is an almost incomprehensible span of geological time. For comparison, the Himalayas began forming around 50 million years ago. The Rocky Mountains were already ancient when this subduction zone was getting started, and over those tens of millions of years, the Pacific plate has been sliding beneath the Philippine Sea plate in a slow, grinding descent, carrying with it not just rock and sediment but seawater. Seawater that has been locked into the oceanic crust through a process called hydration, and that gets released again as the plate descends and heats up. One of the things that happens when that water is released under pressure and heat is a process called serpentinization. It sounds almost mythological, and in a way the chemistry is just as strange as the name suggests. When seawater reacts with certain iron and magnesium-rich rocks in the oceanic mantle, rocks called periddotites, it transforms them into a new mineral called serpentinite, and in doing so it releases hydrogen gas and methane. Not in enormous quantities, but consistently, along the walls and fault zones of the trench, wherever the plate boundary allows mantle material to come into contact with circulating water. Hydrogen and methane are not just chemical curiosities, they are energy sources, and in the deep ocean, where sunlight cannot reach and photosynthesis is impossible, chemical energy is the only alternative foundation for a food web. This is the basis of chemosynthesis, the process by which certain microorganisms use chemical reactions rather than sunlight to produce organic matter. We know that chemosynthetic communities exist in other parts of the world's deep ocean. Cold seeps along continental margins, hydrothermal vents along mid-ocean ridges, and serpentinite-hosted systems in various subduction zones have all been documented to support rich biological communities built on chemical energy rather than solar energy. The Lost City hydrothermal field in the Atlantic, for instance, sits on a serpentinite seafloor and hosts dense microbial mats and communities of shrimp and other invertebrates that owe their existence entirely to the hydrogen and methane produced by serpentinization. In the Ogasawara Trench, chemosynthetic communities have not yet been confirmed. That is an important distinction to hold on to. The conditions that could support them appear to exist. These serpentinization processes are occurring along the trench walls, and the methane and hydrogen they produce are chemically detectable in the water column in some parts of the Isobonin arc system. But whether organisms are actually exploiting those chemical gradients at Hadal depths, and if so, what they look like, remains an open question. The sampling has simply not been thorough enough to answer it. Freefall landers baited with mackerel do not tell you much about chemosynthetic communities. You need different instruments, different sampling strategies, and ideally a vehicle that can move along the trench wall and collect material from specific chemical environments. That kind of targeted survey has not yet been done here. What makes this particularly interesting is the proximity of the volcanic arc. The Izubonin Island chain runs parallel to the trench, separated from it by the Arc Trench Gap, and it is one of the most volcanically active island arcs in the Western Pacific. Submarine volcanoes along this arc, some of them rising from depths of several thousand meters, release hydrothermal fluids that alter the chemistry of the surrounding water. These fluids carry metals, sulfur compounds, and dissolved gases that do not occur in ordinary seawater at those concentrations. And while the main axis of the trench is separated from the volcanic arc by geography, the two systems are connected through the same underlying subduction process. The chemical fingerprints of volcanic and hydrothermal activity have been detected in water samples from the broader Izubonin region, suggesting that the trench environment is not chemically isolated from what is happening in the arc above it. The sediment chemistry adds another layer to this picture. At the depths of the Ogasawara Trench, the seafloor is covered primarily in what geologists call siliceous ooze, a fine, soft sediment composed largely of the skeletal remains of diatoms and radiolarians, microscopic organisms that lived in the surface waters far above and sank slowly to the bottom after death. Diatoms are photosynthetic algae with intricate silica shells, and radiolarians are single-celled animals with similarly elaborate silica frameworks. When they die, their organic matter is mostly consumed on the way down, but their silica shells accumulate on the seafloor over millions of years, building up layers of ooze that can be meters thick. This siliceous ooze is not inert, it is a habitat. The interstitial spaces between the silica particles are occupied by bacteria and archaea, microbial communities that process organic matter, cycle nutrients, and generate chemical gradients that other organisms can exploit. Sediment cores recovered from the Izubonin region have shown that these microbial communities extend meters below the sediment surface, living in conditions of near total darkness, extreme pressure, and very limited energy supply. They metabolize slowly, reproduce slowly, and may live for extraordinarily long periods. Some deep sediment bacteria are thought to have generation times measured in thousands of years. They are not doing nothing. They are cycling carbon, nitrogen, sulfur, and iron through the sediment in ways that shape the chemistry of the overlying water and the availability of nutrients for organisms living at the sediment surface. One thing that distinguishes the Ogasawara Trench from some other Hadal systems is the relatively low flux of organic carbon reaching the sea floor. Organic carbon flux, the rate at which organic material sinks from the surface ocean to the deep, depends heavily on how productive the surface waters are. In regions where cold, nutrient-rich water upwells to the surface, like the Eastern Pacific or the waters around Antarctica, surface productivity is high, and the deep seafloor receives a relatively generous supply of organic material. In the Western Pacific near the Izubonin Arc, surface productivity is lower. The water is warmer and more stratified, nutrients are less abundant at the surface, and the biological pump that carries organic carbon to depth operates less efficiently. What does reach the trench floor has also had a long distance to travel, 9,000 meters or more, during which time much of the organic content is consumed by bacteria in the water column. The result is a trench floor that is, by the standards of Hadal environments, relatively food poor. Not completely barren. There is always some organic material arriving, both as a slow background rain of particles and as occasional larger inputs like the carcasses of whales or fish, or pulses of material delivered by turbidity currents. But the baseline food supply is sparse, and this scarcity is not a neutral fact about the trench. It is one of the most powerful forces shaping what can live there, how large those organisms can grow, how they behave, and how they have evolved. A food-poor environment selects for efficiency. organisms that can extract the maximum energy from minimal resources, that can survive long periods without feeding, that can detect and exploit food sources quickly when they do appear. These are the organisms that persist. This is part of why hadal amphipods are so successful in trenches like Izu Ogasawara. They are extraordinarily efficient scavengers. They can detect the chemical signals of a food source from a considerable distance, converge on it rapidly, consume it almost completely, and then return to a state of low metabolic activity while waiting for the next opportunity. Their bodies are built for this cycle of feast and fast in a way that is genuinely impressive when you consider the conditions they are operating under, but the food scarcity also imposes limits. It is one of the reasons why the hadal zone does not support large, energetically expensive predators in the way that shallower ocean environments do. A large predator needs a reliable food supply. In a trench where organic input is limited and spatially patchy, maintaining the metabolic costs of a large body becomes very difficult. This is part of the argument against the presence of large cephalopods or other big invertebrates at hadal depths. Not just the pressure, but the energetics. The trench cannot easily feed them. What it can feed, and what it does feed, are the smaller, more efficient organisms that have tuned their biology to the specific rhythms of this environment. And here the chemical gradients become relevant again. If serpentinization along the trench walls is releasing hydrogen and methane, and if chemosynthetic bacteria are using those chemicals as energy sources, then there is a potential food web operating in the trench that is entirely independent of the surface ocean's productivity. A community built on chemical energy does not need the sun to shine above it. It does not depend on seasonal blooms of diatoms or on the slow rain of organic particles from the surface. It runs on geology. And geology in the Isobonin-Mariana system is not in short supply. This is speculative in the specific context of the Izu Ogasawara Trench, because the evidence for active chemosynthetic communities here is not yet conclusive. But it is not idle speculation. It is a hypothesis grounded in the known chemistry of the trench walls, the known biology of similar environments elsewhere, and the known capacity of deep-sea life to exploit chemical gradients that surface organisms would never encounter. The question is not whether chemosynthesis could operate in the Izu Ogasawara Trench. The chemistry suggests it could. The question is whether it does, and at what scale, and what organisms are involved. Answering that question requires sampling from the trench walls specifically, not just from the flat sediment floor at the bottom, where most lander deployments are aimed, but from the steep, geologically active flanks where serpentinization and fluid seepage are most likely to occur. Those walls are difficult to sample. They are steep, structurally complex, and in some places actively unstable. A freefall lander cannot be deployed against a vertical wall. You need a vehicle that can navigate laterally, hold position against currents, and collect targeted samples from specific locations. The Shinkai 6500 can do some of this, but its depth limit of 6,500 meters means it cannot reach the deepest parts of the trench walls. The tools that could answer this question have not yet been deployed here in the way that the question requires. So the chemistry of the Izu Ogasawara Trench sits in an interesting position, partially understood, clearly distinctive, and pointing toward biological possibilities that have not yet been confirmed or ruled out. The serpentinization is real. The methane and hydrogen are detectable. The volcanic arc is active and chemically influential. The sediment is siliceous and microbially rich. The organic carbon flux is low, which shapes everything that lives on the trench floor. These are not vague impressions. They are documented features of the trench's chemical environment, and they matter for understanding what kind of life this place can support. What they collectively suggest is a trench that is chemically more complex than its depth and remoteness might imply. A place where multiple energy sources, multiple chemical gradients, and multiple geological processes are operating simultaneously, creating a patchwork of microenvironments that different organisms can exploit in different ways. The amphipods on the sediment floor, the microbial communities in the ooze, the potential chemosynthetic bacteria on the trench walls, the organisms that might be exploiting hydrothermal influence from the arc above. These are not all living in the same environment. They are living in adjacent but chemically distinct niches within the broader system of the trench, and all of this is happening under conditions of scarcity and pressure and darkness that would be lethal to almost anything alive on the surface of the Earth. Which brings us back to the central question that the biology keeps raising. How exactly does life manage to exist here at all? The chemistry gives part of the answer. There are energy sources available if you know how to use them. But the mechanisms by which living organisms actually function under 900 atmospheres of pressure in near-freezing water in the complete absence of light are remarkable in their own right. The adaptations that make Hadal life possible are not minor adjustments to the standard biological toolkit. They are deep, fundamental modifications to the way cells work, proteins fold, membranes flex, and metabolism runs. And understanding those adaptations turns out to be one of the most illuminating things that deep-sea biology has produced. Not just for what it tells us about life in trenches, but for what it reveals about the limits and flexibility of life itself. So let us stay with that question for a moment, because it is genuinely one of the more fascinating corners of modern biology. The adaptations that allow organisms to survive at Hadal depths are not just interesting in a general sense. They are specific, measurable, and in some cases counterintuitive. They involve changes at the molecular level that are only now being understood well enough to explain, and they reveal something important about how flexible the chemistry of life actually is when the environment demands it. The starting point, when biologists talk about pressure adaptation in deep-sea organisms, is usually a molecule called trimethylamine oxide. The name is a mouthful, and it is usually shortened to TMAO. If you have ever noticed a faint oceanic smell on certain fish, TMAO is partly responsible for that, but its role in the bodies of Hadal animals is something quite different from flavouring. At depth, the pressure exerted on living tissue is so extreme that it begins to physically distort the shape of proteins. And proteins, in biology, are almost entirely defined by their shape. An enzyme that is supposed to catalyse a specific chemical reaction does so because its three-dimensional structure fits its target molecule in a precise way. Distort that structure and the enzyme stops working. At 900 atmospheres of pressure, proteins in a surface-dwelling organism would be deformed to the point of dysfunction. The animal would simply stop working at the cellular level. TMAO counteracts this. It acts as what biochemists call a piezolyte, a pressure-stabilizing molecule that accumulates in cells and physically counteracts the tendency of proteins to be compressed and distorted under high pressure. It essentially props the protein structure open against the weight of the water above. And what researchers have found, looking at amphipods and snailfish collected from Hadal depths, is that the concentration of TMAO in their tissues scales almost linearly with the depth at which they live. Shallow water fish have low TMAO concentrations. Fish living at 3,000 metres have more. Fish at 8,000 metres have concentrations that are dramatically higher. High enough, in fact, that the TMAO itself begins to impose limits on how the cells function. This is one of the reasons behind what some researchers call the 8,200 metre barrier for fish. The hypothesis, developed partly through the work of Paul Yancey at Whitman College and his collaborators, is that beyond a certain depth, the TMAO concentration required to stabilize proteins against pressure becomes so high that it creates its own physiological problems. The cells become saturated with the molecule. At some point, you cannot add more without disrupting other processes. The result, if the hypothesis holds, is a depth ceiling for vertebrate life. Not because the pressure is too great in a purely mechanical sense, but because the chemical solution to the pressure problem runs out of room to scale. The deepest confirmed fish observation, a snailfish recorded at 8,336 metres in the Ogasawara Trench in 2023 by a joint team using baited camera systems, sits very close to that predicted limit. Whether any vertebrate can survive below that depth remains an open question. The trench goes considerably deeper than 8,336 metres. Amphipods, being invertebrates with a different body plan and different biochemistry, are not subject to the same TMAO sealing in the same way, which is part of why they can be found at the very bottom of the deepest trenches. Their pressure adaptations involve TMAO as well, but also other mechanisms that give them more flexibility. One of the most important is what happens to their cell membranes. Every living cell is enclosed in a membrane made largely of lipids, fatty molecules that form a flexible bilayer. That flexibility is essential. The membrane needs to allow certain molecules to pass through it, to support protein structures embedded within it, and to maintain its integrity under the forces acting on it. At high pressure and low temperature, membranes become stiffer and less permeable. This is a problem. A cell membrane that has become too rigid cannot function properly. It is like trying to work with a material that has gone from rubber to glass. Hadal organisms compensate by increasing the proportion of unsaturated fatty acids in their membranes. Unsaturated fatty acids have a different molecular geometry. Their carbon chains have kinks in them, which prevent the molecules from packing together as tightly. More unsaturated fats means a more fluid, more flexible membrane even at high pressure and low temperature. It is a relatively simple chemical adjustment, but it has to be maintained continuously, and it requires the organism to either synthesize these fatty acids itself or obtain them from its diet. Deep-sea amphipods, as it turns out, accumulate polyunsaturated fatty acids at concentrations that are quite high compared to their shallow water relatives. Their bodies are, in a sense, chemically tuned to stay soft in an environment that would otherwise freeze and compress them toward rigidity. Metabolic slowdown is another piece of the picture. At temperatures of 1 to 2 degrees Celsius, the chemical reactions that drive metabolism proceed more slowly. This is not unique to Hadal organisms. It is a basic feature of chemistry that reaction rates decrease with temperature. But Hadal animals have adapted to operate within this slower metabolic regime rather than fighting against it. Their enzymes are calibrated to function efficiently at low temperatures, which is actually a distinct adaptation from surface-dwelling organisms whose enzymes are optimized for temperatures around 20 to 37 degrees Celsius. A Hadal amphipod's metabolic enzymes would be sluggish and inefficient if you warm the animal up. They are not designed for warmth. They are designed for cold, and they work well there. This metabolic economy is part of what allows these animals to survive long periods between food events. They are not burning energy quickly. They are running on a slow, efficient cycle that keeps them alive through the dark intervals between meals. And then there are the meals themselves, which are worth describing because the behaviour is striking. When a food source arrives on the Hadal floor, whether it is a baited trap deployed by researchers, a dead fish that has sunk from above, or a larger carcass, the response from the local amphipod population can be almost immediate. Lander footage from the Izubonin region and from other Hadal trenches has shown swarms of amphipods converging on bait within minutes of it reaching the bottom. Within a few hours, a significant piece of fish can be reduced to bone. The numbers involved are sometimes in the hundreds or even thousands of individuals, all arriving from the surrounding sediment in a coordinated-looking rush that is actually just the independent response of many individuals to the chemical signal of food diffusing through the water. This behaviour makes sense when you consider the scarcity of the environment. Food at Hadal depths is rare and unpredictable. When it arrives, the organisms that can find it fastest and consume it most efficiently are the ones that survive and reproduce. The amphipod's chemosensory abilities, their capacity to detect dissolved organic compounds in the water at extremely low concentrations, are finely tuned for exactly this purpose. Their feeding apparatus is efficient and rapid, and once the food is gone, they disperse back into the sediment and resume their low-energy waiting state. It is a boom and bust feeding strategy that mirrors the boom and bust nature of food availability in the Hadal zone. The biology matches the environment with a precision that is one of the things that makes Hadal ecology genuinely interesting to study. even when the conditions for studying it are so difficult. One thing that comes up in conversations about the deep sea, and that is worth addressing carefully here, is bioluminescence. The deep ocean is famous for it. The glowing lures of anglerfish, the blue flashes of dinoflagellates, the red photophores of certain shrimp. Bioluminescence is one of the most visually striking features of deep-sea life, and it is remarkably widespread in the mesopelagic zone, between roughly 200 and 1,000 metres. But whether it occurs in the Hadal zone, below 6,000 metres, is less clear. The organisms most commonly associated with bioluminescence, certain fish, squid, jellyfish and crustaceans, are not typically found at Hadal depths. The Hadal zone is dominated by amphipods, polychaete worms, holothurians and foraminifera, none of which are known for producing light. Some researchers have suggested that bioluminescence would be of limited value in the Hadal zone anyway, because the community is sparse enough that the communication and predator attraction, functions that light serves in shallower communities, would be less relevant. Others point out that we simply have not observed the Hadal zone closely enough, or for long enough, to know what light-producing behaviours might occur there. The cameras on lander systems are typically equipped with their own artificial lighting, which would outshine any bioluminescence present and make it invisible to the recording equipment. It is one of those questions that is technically answerable but has not yet been answered, because the right observation has not been made in the right way. What has been observed, and what is worth lingering on, is the sheer physiological elegance of Hadal organisms when you look at them closely. These are not primitive or degraded creatures. They are not simplified versions of their shallow water relatives, stripped down to bare functionality by a harsh environment. In many respects, they are more biochemically sophisticated than organisms living under easier conditions, because they have had to solve problems that simply do not exist at the surface. The TMAO system, the membrane lipid adjustments, the cold active enzymes, the chemosensory precision, the metabolic economy, these are not absences of complexity, they are additions to it. They are solutions to problems that required evolutionary time and biological ingenuity to develop. The Hadal zone has been present on Earth for tens of millions of years, and the organisms living in it have had that entire span to refine their adaptations. What we are looking at, when we look at a Hadal amphipod, is the product of an enormously long process of biological problem-solving conducted in complete darkness, at the bottom of one of the deepest places on the planet. There is also something worth noting about what the TMAO research in particular has meant for biology beyond the deep sea. Understanding how pressure affects protein structure, and how TMAO counteracts that effect, has opened lines of inquiry into protein folding more broadly, a topic that is central to medicine, to the understanding of diseases like Alzheimer's that involve misfolded proteins, and to the design of enzymes for industrial applications. The Hadal zone has contributed to human biochemistry, not because anyone went looking for medical insights in a trench 9 kilometers deep, but because the organisms living there had evolved solutions to a version of a problem that turns out to be relevant far beyond their particular environment. This is one of the arguments that conservation biologists and deep-sea researchers make when they talk about the importance of studying places like the Ogasawara Trench. The biological knowledge locked in these organisms is not abstract. It has applications, and it is inaccessible until the organisms themselves are studied. The pressure limit for fish, the lipid chemistry of amphipod membranes, the cold active enzymes, all of these are things we know because researchers made the considerable effort to collect and analyse organisms from Hadal depths. Every additional species, every additional sample from a trench like Ogasawara has the potential to add to that picture. And given that the Ogasawara Trench has been sampled so sparsely compared to its actual size, the organisms living there that have never been collected, never been described, never had their biochemistry analysed. They represent a genuine gap in our understanding. Not a romantic gap, not a mysterious gap in the vague sense, but a specific, measurable gap in scientific knowledge that has real consequences for what we understand about how life works under extreme conditions. All of which makes the next part of the Trench's story both relevant and a little sobering. Because the biology of the Ogasawara Trench is not shaped only by pressure and temperature and food scarcity and chemical gradients. It is also shaped by geology, by the same subduction zone that built the trench in the first place, and that continues to operate beneath it with the kind of slow, enormous force that occasionally expresses itself in ways that are anything but slow. The trench is not a static container for its biology. It is an active geological system, and the events it generates reshape the environment in which its organisms live, sometimes dramatically, sometimes catastrophically, and sometimes in ways that actually deliver something the deep community needs. The earthquakes that the subduction zone produces are not just seismic events recorded on instruments at the surface, they reach the trench, and when they do, they change things. The subduction zone beneath the Ogasawara Trench is not a quiet mechanism. It is one of the most seismically active convergent margins on the planet, and it has been generating earthquakes for tens of millions of years. The Pacific Plate does not slide smoothly beneath the Philippine Sea Plate. It moves in fits and holds, accumulating stress along the fault interface until that stress exceeds what the rock can bear, and then it releases, sometimes gradually, sometimes all at once, in events that send shock waves through thousands of kilometers of ocean floor. The surface world knows these events as earthquakes. The trench knows them as something more immediate and more physical. A sudden rearrangement of the environment, a cascade of sediment, a pulse of energy moving through water and rock that has no parallel in any shallow water ecosystem. To understand what this means for the biology of the trench, it helps to think about what the walls of the Ogasawara Trench actually look like. They are not smooth slopes. Multi-beam sonar mapping has revealed them to be steep, irregular, scarred by old landslide scars and fresh-looking debris aprons at their bases. Material accumulates on those walls over time. Sediment carried by currents, organic particles drifting down from the surface, fine clay settling slowly through the water column over centuries, and then, when a large earthquake occurs, some of that material moves. It does not drift, it flows. The technical term is turbidity current. When sediment on a steep underwater slope is destabilized, by seismic shaking, by the sudden addition of too much new material, or by changes in pore water pressure, it can mobilize into a dense, fast-moving slurry that rushes downslope, carrying with it everything that was resting on that section of wall. These flows can travel at tens of kilometers per hour. They can carry enormous volumes of material. And when they reach the floor of the trench, they deposit that material in layers, sometimes thin, sometimes thick, sometimes burying whatever was living there beneath a blanket of sediment that arrived with almost no warning. The 2011 Tohoku earthquake, which struck off the coast of northeastern Japan at a magnitude of 9.0, generated exactly this kind of event in the Japan Trench. Researchers analysing sediment cores taken from the Japan Trench floor after the earthquake found evidence of a significant turbidite, a layer of sediment deposited by a turbidity current that had been triggered by the quake. The layer was distinctive, coarser material at the base, grading upward to finer particles as the flow decelerated, exactly the signature that geologists look for when identifying turbidite deposits. It was, in essence, a geological record of the earthquake written in the sediment of the trench floor. The Ogasawara Trench sits within the same broad tectonic system, driven by the same subduction geometry, and there is every reason to believe that large earthquakes in this region produce similar effects along its walls and floor. The 1703 Genroku earthquake, which struck the Sagami Trough at the northern end of the Izubonin Arc, and is estimated to have reached a magnitude of around 8.2, would have sent significant seismic energy into the adjacent trench system. Historical records from that event describe massive coastal changes, shorelines that rose by several meters in some places, harbours that became unusable overnight, which reflect the scale of seafloor displacement involved. What happened at depth during that event is not recorded in any historical document. No instrument was in place to capture it. But the sonar maps of the trench walls, with their visible scarring and debris accumulation, carry a kind of geological memory of events like that one, even if the specific attribution is difficult. What makes turbidity currents particularly interesting from a biological standpoint is that they are not only destructive, they are also, in a certain sense, generous. The material they carry downslope includes organic carbon, particles of dead phytoplankton, fragments of zooplankton, bits of organic matter that had been resting on the shelf or the upper slope waiting. When a turbidity current mobilizes that material and delivers it to the Hadal floor, it represents a sudden, concentrated pulse of food arriving in an environment where food is normally extremely scarce. The deep trench floor is not a productive place in the conventional sense. Surface productivity in the Western Pacific above the Ogasawara Trench is moderate at best, and the organic material that sinks from the surface has a long distance to travel before it reaches 9,000 meters. Much of it is consumed or decomposed along the way. What arrives at the trench floor under normal circumstances is a slow, thin rain of particles, enough to sustain microbial communities and small deposit feeders, but not abundant by any measure. A turbidity current changes that equation abruptly. A single large event can deposit more organic material on the trench floor in a matter of hours than would otherwise arrive over months or years. For organisms adapted to exploit sudden food availability, and Hadal amphipods are very much in that category, capable of swarming a food source within hours of its arrival, a turbidity current deposit is an opportunity. It is a feast delivered by catastrophe. There is something almost counterintuitive about this. The same geological event that can bury sections of the trench floor, destroying whatever community was established there, can simultaneously enrich other sections with organic material that would not otherwise have reached them. The trench is not a uniform environment. It has patchiness, areas of relative abundance and areas of relative scarcity, shaped in part by the history of geological events that have occurred along its length. A section of the floor that received a large turbidite deposit 50 years ago might still be processing that organic material, supporting a denser community than sections that have not received such input recently. The biology of the trench is, in this sense, a record of its geological history, written not in sediment layers, but in the distribution and density of its living communities. Mass-wasting events, the broader category of underwater landslides and slope failures of which turbidity currents are one type, are visible in the sonar data from the Ogasawara Trench walls. There are amphitheatre-shaped scars on the upper walls where large sections of sediment have detached and moved downslope. There are debris lobes on the lower walls and at the base of the inner trench slope where that material came to rest. Some of these features are old enough to be partially resedimented, suggesting they occurred long ago. Others look fresher, with sharper edges and less in filling, though dating them precisely without sediment cores is difficult. The trench walls are, geologically speaking, an active surface, not stable, not finished, not settled into a permanent configuration. They are a work in progress, and the organisms that live on them have to contend with that instability as part of their environment. Beyond the turbidity currents and slope failures, there is another category of food delivery to the deep trench that operates on a different timescale and a different mechanism entirely. These are what deep-sea biologists call food falls, the arrival of large organic objects at the seafloor. The most studied of these are whale falls, the bodies of large whales that sink to the bottom after death and become, over a period of years or even decades, an enormously rich food source for deep-sea communities. A single large whale carcass can deliver as much organic carbon to the seafloor as would otherwise arrive via the slow particle rain over a century. The communities that develop around whale falls pass through distinct stages. First, mobile scavengers like hagfish and sleeper sharks stripping the soft tissue, then enrichment opportunists colonising the exposed bones and sediment, and finally sulfophilic bacteria breaking down the lipids in the bones and releasing hydrogen sulfide, which supports a chemosynthetic community similar in some respects to a hydrothermal vent. Whether whale falls occur in the Ogasawara Trench specifically is not well documented. The trench is deep enough that a whale sinking in the waters above it could, in principle, reach the floor, though the hadal depth of the deeper sections would be unusual for a whalefall community, since most documented whalefalls are at abyssal depths between 2,000 and 4,000 metres, rather than hadal depths below 6,000. Woodfalls, the arrival of large pieces of terrestrial wood, carried to sea by rivers and eventually waterlogged enough to sink, are another category, and these have been documented at depths approaching the hadal zone in some regions. The Izubonian island chain sits in a region with some terrestrial vegetation, and it is at least possible that wood falls reach the upper portions of the trench walls, though whether they penetrate to the deeper sections is unclear. The broader question these food sources raise is whether the Ogasawara Trench receives enough organic input across all these mechanisms to support larger or more complex organisms than the amphipods and holothurians that have been documented there. This is not a trivial question. The size and complexity of the organisms a deep-sea community can support is ultimately constrained by energy availability. A trench with low organic carbon flux, meaning little food arriving from the surface, few turbidite pulses, no nearby productive upwelling zones, will tend to support smaller, slower, more energy-efficient organisms. A trench with higher flux can potentially support a more complex food web, with larger predators occupying higher trophic levels. The Ogasawara Trench is not particularly well positioned for high organic input under normal conditions. The surface waters above it are not among the most productive in the Pacific. There is no major river system delivering terrestrial organic matter to the region. The trench is long and narrow, and its position in the typhoon corridor of the Western Pacific means that surface mixing can be intense seasonally, but this does not necessarily translate into higher deep export. By comparison, trenches near highly productive coastal upwelling zones or near major river deltas tend to receive substantially more organic material. The Ogasawara Trench is, in terms of its food budget, a relatively lean environment, and yet the turbidity current mechanism means that this is not the whole picture. The geological activity of the subduction zone delivers periodic pulses that can temporarily transform the food landscape of the trench floor. These pulses are unpredictable in timing and variable in magnitude, but they are real, and they have almost certainly shaped the evolutionary strategies of the organisms that live there. An organism that can wait, that has low metabolic rate and can persist through long periods of scarcity, and that can also respond rapidly when abundance arrives, is well suited to exactly this kind of environment. Hadal amphipods match that description almost perfectly. Whether larger organisms have evolved similar strategies in this trench is one of the things that has not yet been determined, because the trench has not been observed closely enough, or for long enough, to answer that question with any confidence. What the geological record of the trench does confirm in the sediment layers and the sonar-visible scars on its walls is that the Ogasawara Trench has been through a great deal. It is not a quiet place, even at 9,000 metres. The subduction zone that created it continues to operate. The earthquakes it generates continue to reshape the walls and floor. The turbidity currents continue to move material downslope in sudden flows that arrive without warning and deposit their cargo on a community that has no means of anticipating them. The trench is, in this sense, a place where catastrophe and sustenance are delivered by the same mechanism, often at the same moment, in proportions that vary unpredictably across space and time. For the organisms that have made this environment their home over millions of years, these conditions are not exceptional. They are simply the terms of existence. The trench has always been like this, geologically active, seismically restless, episodically generous and episodically destructive, and always, always deep. Whatever lives there has evolved not in spite of these conditions but within them, shaped by them, dependent on them in ways that we are only beginning to understand. The turbidity currents that deliver organic material to the floor are not accidents. They are part of the ecology of the place, as much as the pressure and the cold and the darkness. They are part of what makes the Ogasawara Trench the particular kind of environment it is, and part of what makes the organisms that survive there the particular kind of organisms they are. Which brings the question back to what exactly those organisms might be. The amphipods and holothurians and polychaeta worms that have been documented there are the known inhabitants, the ones that lander cameras have filmed and trap systems have collected. But the trench is large and the sampling is sparse, and the turbidity current deposits and whalefall oases and chemosynthetic patches that might exist along its length represent microhabitats that have almost certainly never been directly observed. If the trench harbours things that have evolved specifically to exploit those rare moments of geological abundance, organisms adapted not to the steady lean baseline but to the episodic pulse, they may be things that no standard lander deployment, baited with mackerel and left on the floor for a few hours, would ever encounter. They would be things that require different methods, different timing, different luck. And that is precisely the kind of possibility that makes the next question about what larger or more complex life might plausibly exist in this trench worth asking carefully and without rushing to an answer. So let us ask that question carefully. What larger or more complex life might plausibly exist in the Ogasawara Trench, not as speculation dressed up as fact, but as a genuine scientific possibility grounded in what comparative biology and the evidence from other trenches actually suggest? The first thing worth acknowledging is what probably does not exist there. Giant squid, for instance, are sometimes imagined in connection with the deep ocean, and they are genuinely remarkable animals. Architeuthis ducks can reach lengths of around 13 metres and has been recorded at depths approaching 1,000 metres. But the Hadal zone is almost certainly beyond their range. Giant squid are active, fast-moving predators with high metabolic demands, and the chemistry of the Hadal environment, particularly the pressure constraints on protein function, makes it very unlikely that large cephalopods of that kind have colonised depths below 6,000 metres. The same logic applies to giant isopods, those armoured crustaceans that look like something out of a natural history illustration and that have captured public attention in recent years. Bathynomus giganteus, the largest known species, reaches lengths of around 45 centimetres and lives at depths between 170 and 2,140 metres. That is deep, but it is nowhere near Hadal. The pressures below 6,000 metres appear to present barriers that large isopods have not crossed, at least not in any form that has been documented, so the trench is probably not home to enormous creatures in the way that imagination sometimes fills unknown places. That is worth saying plainly. But the absence of giants does not mean the absence of complexity, and it does not mean the absence of things that would genuinely surprise us. Deep-sea gigantism is a real phenomenon, though its causes are still debated. In some lineages, organisms living at depth grow larger than their shallow water relatives, the giant isopod being one example, certain giant amphipods being another. Alicella gigantea, a deep-sea amphipod, reaches lengths of around 34 centimetres, making it many times larger than most surface-dwelling amphipods. It has been found in the North Pacific at depths between 4,500 and 8,000 metres. Whether something analogous to Alicella gigantea exists in the Ogasawara Trench is genuinely unknown. The trench has not been sampled thoroughly enough to rule it out. Lander trap systems recover what enters the traps, and trap design constrains what can be caught. A large, slow-moving organism that approaches bait cautiously, or that arrives after the lander has already been retrieved, would never appear in the data. Its absence from the record would tell us nothing about its actual presence or absence in the trench. The snailfish question is perhaps the most scientifically tractable one. In the Mariana Trench, Pseudoleparis sweari was formally described in 2017 based on specimens collected at depths of 7,498 to 8,178 metres. Before that formal description, snailfish had been observed in Mariana lander footage for years without being named. The Kermadec Trench has its own snailfish population. The Atacama Trench has another. Each trench appears to have its own endemic snailfish lineage, shaped by the isolation of the Hadal environment. Given this pattern, the expectation among Hadal biologists is that the Izu Ogasawara Trench almost certainly has its own snailfish species, or had one, or has one that has simply not yet been collected in a condition suitable for formal taxonomic description. Lander footage from the Izubonin region has captured elongated fish at depth, but the footage quality and the angle of observation have not always been sufficient to make a definitive identification. These are not dramatic mystery sightings. They are the ordinary frustrations of working at 9,000 metres with cameras mounted on a frame that you cannot steer, in water that is not perfectly clear, observing animals that do not cooperate with documentation. The fish are probably there. Whether they are a distinct species or a population of something already described from a neighbouring trench is a question that requires specimens. And getting specimens from this depth is genuinely hard. The physical limit of fish at Hadal depths is a question that has received serious scientific attention. The hypothesis, developed partly through the work of researchers including Paul Yancey at Whitman College, is that the concentration of trimethylamine oxide in fish tissues, the compound that stabilizes proteins against pressure denaturation, imposes a ceiling on how deep fish can survive. The argument runs roughly as follows. TMAO concentration must increase with depth to maintain protein function, but beyond a certain concentration, TMAO itself begins to interfere with cellular processes. The estimated limit falls somewhere around 8,200 metres, though some researchers put it slightly higher. If this hypothesis is correct, then no fish species, anywhere in any trench, can be viable much below that depth. The deepest confirmed fish record stands at 8,336 metres. A snailfish observed in the Izubonin Trench in 2023 by a team using a lander system deployed by researchers from the University of Western Australia and Tokyo University of Marine Science and Technology. That record is worth pausing on. It was set in this trench. Not the Mariana, not the Kermadec, but the Izu Ogasawara Trench specifically. The fish observed was a snailfish, pale and translucent in the camera light, moving slowly near the sediment surface. It was not formally identified to species at the time of the initial announcement, and the question of whether it represents a known or unknown species remains open. What the observation confirms is that the Izu Ogasawara Trench is capable of supporting vertebrate life at extraordinary depth, and that the snailfish living there may be operating at or near the absolute physical limit for fish on this planet. There are also the historical accounts, which are harder to evaluate but worth mentioning. Japanese fisheries records from the Izubonin region, a broad area that includes the waters above and around the trench, contain occasional references to unusual catches and unusual observations going back several decades. Longline fishing in this region operates at depths that can reach several hundred metres, nowhere near the Hadal zone, but the accounts occasionally describe creatures that did not match familiar species. These records are fragmentary and vague, and it would be a mistake to treat them as evidence of specific unknown organisms. Deep-sea fishing produces strange encounters regularly, and the line between a genuinely unusual animal and an unusual individual of a known species is often impossible to draw from a fisherman's description alone. What the records do suggest is that the waters of the Izubonin region have been producing surprises for a long time, and that the surface fishery, operating in the upper water column, is not particularly well positioned to tell us anything definitive about what lives at 9,000 metres below. What comparative biology does tell us, with reasonable confidence, is that the Izu Ogasawara Trench is likely to contain endemic species across multiple taxonomic groups. The pattern of Hadal endemism, the tendency for each trench to have its own distinct fauna, shaped by isolation and local conditions, is well established enough that its application to this trench is not really speculative. It is the expected outcome based on what has been found everywhere else. The question is not whether endemic species exist in the Ogasawara Trench, but how many, across which groups, and with what characteristics. Amphipods almost certainly have endemic species there. The genetic divergence between Izubonin populations and Mariana populations has been noted in the limited sampling that has been done. Polychaete worms, which are diverse and abundant in Hadal sediments globally, are likely to have undescribed species in this trench. Foraminifera, the single-celled organisms that build elaborate shells and are found throughout the deep ocean, have been documented in Izubonin trench sediments, and some forms collected there have not been matched to previously described species. Then there is the dark biosphere. This term refers to the microbial communities that live not on the surface of the seafloor, but within the sediment itself, sometimes to depths of tens of meters below the sediment-water interface. These communities are largely chemosynthetic. They derive energy not from organic material falling from above, but from chemical reactions involving compounds in the sediment. In terms of raw biomass, the dark biosphere may represent a substantial fraction of all living matter on Earth, though estimates vary widely, and the field is still developing. In the Ogasawara Trench, the sediment column has been cored in a limited number of locations, and the microbial communities found there are not well characterized. The trench's position near the Izubonin volcanic arc means that the sediment chemistry may support unusual microbial metabolisms, hydrogen-oxidizing bacteria for instance, or sulfur-cycling communities in zones where serpentinization reactions are producing reduced compounds. Whether any of these microbial communities support larger organisms through chemosynthetic food webs, as happens at hydrothermal vents and cold seeps in other parts of the ocean, is not known. The conditions for such communities may exist in the trench, but no systematic search for them has been conducted. A full survey of the Ogasawara Trench, if one were ever mounted with the resources and technology it would require, would probably reveal a picture considerably more complex than what current data suggest. The realistic expectation, based on what has been found in better studied trenches, is multiple undescribed species of amphipods, polychaete worms, and holothurians. At least one endemic snailfish species, possibly undescribed species of smaller crustaceans and mollusks, unusual microbial communities in the sediment, and potentially chemosynthetic patches associated with fluid seepage along the trench walls. None of this is guaranteed, but none of it is implausible either. It is the kind of inventory that emerges consistently when Hadal environments are examined carefully and over time. The Ogasawara Trench has not been examined carefully or over time. It has been sampled at a handful of points, with instruments that capture a narrow slice of what is actually there, during expeditions that were often focused on geological rather than biological objectives. The honest summary is this: the trench almost certainly contains organisms that have never been formally described, and very likely contains organisms that have never been observed at all. Whether any of those organisms are large enough or visually striking enough to attract wide attention is a separate question. The most significant discoveries may well be small: a new amphipod species, a new polychaete, a microbial lineage with unusual biochemistry. Science does not require drama to be meaningful. A new species of worm living at 9,000 meters in a trench that most people have never heard of is, in its own way, an extraordinary thing. It means that life has found a way into one of the most extreme environments on this planet and has done something new with it, something distinct from what life has done in every neighbouring trench, shaped by the particular pressures and temperatures and chemical conditions of this specific place. That is not a small thing, even if it does not photograph particularly well. What a future full survey might realistically find, in terms of larger organisms, remains genuinely open. The 2023 snailfish observation suggests that vertebrate life is present and active at record depths in this trench. Whether that individual, or others like it, belongs to an undescribed species is a question that requires a specimen. Getting that specimen, catching or collecting an animal at 8,336 meters in good enough condition for taxonomic analysis, is a significant technical challenge, but it is not an impossible one. Lander trap systems have recovered snailfish from comparable depths in other trenches. The technology exists. What has been missing, in the case of the Ogasawara Trench, is the sustained attention and the dedicated resources to apply that technology systematically across the trench's full length and depth range. That sustained attention may eventually come, and when it does, the trench will almost certainly have things to show us that we were not expecting. The history of Hadal exploration has been, consistently, a history of surprises, of animals found where they were not predicted, of behaviours observed that did not match prior assumptions, of biochemical adaptations that pushed the known limits of what biology can do. The Ogasawara Trench, less visited than its neighbours, less familiar than the Mariana, has had fewer opportunities to produce its surprises. They are presumably still waiting there, in the dark, at pressures that would destroy any unprotected human instrument, in water barely above freezing, in a place where the nearest sunlight is nearly 10 kilometres straight up. But the trench does not exist only in biological terms, it exists in human terms as well, and the human story layered into this place, the history that the deep water has absorbed from the surface world above it, is its own kind of record, quiet and strange and worth examining. The water above the Ogasawara Trench has seen a great deal of human history. That is easy to forget when you are thinking about amphipods and snailfish and the dark biosphere. The trench feels so remote, so outside ordinary human experience, that it is tempting to imagine it as a place entirely separate from the surface world and its events. But the surface world has been busy above this trench for a long time, and some of what happened there has found its way down. The Izubonin region, the stretch of western Pacific Ocean above and around this trench, was one of the most heavily contested maritime corridors of the Second World War. In June of 1944, the Battle of the Philippine Sea was fought in waters that extended across this part of the Pacific, in an engagement that became one of the largest carrier battles in naval history. American and Japanese carrier groups clashed over several days, and the losses were substantial. The Japanese Navy lost 3 aircraft carriers, the Taiho, the Shokaku and the Hio, along with hundreds of aircraft and thousands of men. American forces lost far fewer ships, but still suffered significant aircraft casualties. The battle was so one-sided in terms of aircraft losses that American pilots nicknamed it the Great Marianas Turkey Shoot, though the Izubonin waters were part of the broader operational theatre. What this means in practical terms is that aircraft went into the water, ships went into the water, men went into the water. The seafloor of the Western Pacific in this region is not empty of human material. Some of what was lost in 1944 settled at depths far beyond any recovery effort. Not in the trench itself necessarily, but in the deep water surrounding it, in the abyssal plains that flank the trench walls. The exact resting places of many aircraft and smaller vessels from this period have never been determined. The water is too deep, the area too vast, and the documentation from the chaos of combat too incomplete. Japanese Imperial Navy vessels operated extensively in the Izubonin corridor throughout the war, using the island chain as a staging ground and defensive line. Chichijima and Iwo Jima, islands that sit along the Ogasawara Arc directly above the southern portion of the trench, were heavily fortified Japanese positions. The fighting around these islands, particularly the Battle of Iwo Jima in February and March of 1945, sent additional material into the surrounding deep water. Transport ships, patrol vessels and smaller craft were lost in these waters during years of intense naval activity, and many of them have never been located. This is not an unusual situation for the Pacific. The ocean floor across a wide swathe of the Western Pacific is, in a sense, an unacknowledged archive of the mid-20th century. But the Ogasawara Trench's particular depth makes it a permanent archive. Nothing placed in water 9 kilometres deep is coming back up. The pressure alone would destroy most materials over time, but metals corrode slowly in cold, low-oxygen, deep water, and some structural remnants persist for decades or longer. Whether any wreck material has come to rest in the Hadal zone of the trench itself, below 6,000 metres, is not documented. The logistics of searching for wrecks at those depths are even more prohibitive than the logistics of biological sampling. After the war ended, the Deep Pacific became for a period a disposal site. This is documented in both American and Japanese records, and it is not a comfortable part of the history. Chemical weapons, including mustard gas shells and other agents produced during the war, were disposed of at sea by multiple nations in the years following 1945. The United States alone disposed of approximately £64 million of nerve and mustard agents in the ocean between 1944 and 1970, according to a 1998 report by the US Army. Much of this was concentrated in designated dump sites, but the Western Pacific received a portion of this material. Japan also disposed of chemical munitions at sea, including in waters near the Izubonin region, as documented in post-war records and subsequent environmental surveys. The munitions that were dumped in relatively shallow water, a few hundred metres, have in some cases been studied and are known to be corroding and leaking. The munitions disposed of in very deep water are largely unmonitored. What the long-term chemical effects of corroding shells at depth might be on the surrounding biology is not well understood. The concentrations involved, dispersed across vast volumes of deep water, may be too low to produce measurable biological effects, or they may not be. The honest answer is that nobody has looked carefully enough in the right places to know. What has been studied more carefully, and what has produced some genuinely disturbing results, is the contamination of Hadal organisms by persistent organic pollutants, compounds that were not dumped intentionally into the deep ocean, but arrived there anyway, carried by ocean currents and atmospheric deposition from the surface world. In 2017, a research team led by Alan Jameson at Newcastle University published findings from amphipods collected in two of the deepest trenches in the world, the Mariana Trench and the Kermadec Trench, northeast of New Zealand. The amphipods were tested for polychlorinated biphenyls, known as PCBs, and polybrominated diphenyl ethers, known as PBDS, industrial chemicals that were widely manufactured and used throughout the 20th century and are now banned or heavily restricted in most countries. The results were striking. PCB concentrations in the Mariana amphipods were found to be 50 times higher than in crabs living in one of China's most polluted rivers. The Kermadec amphipods showed similarly elevated levels. These are not small exceedances. They are concentrations that, in surface animals, would be considered severely contaminated. The chemicals had arrived in the Hadal zone through a process that researchers describe as a combination of direct sinking of contaminated particles and the consumption of contaminated organic material by animals that then died and sank, carrying the pollutants with them to the seafloor. Once there, the chemicals accumulated in the fat-rich tissues of Hadal amphipods, which have high lipid content as an adaptation to the cold and pressure. Samples from the Izubonin region, while less extensively analysed than those from the Mariana or Kermadec, have shown similar patterns in the data that does exist. The trench is not isolated from this contamination simply by virtue of being less studied. The ocean currents that flow through the Western Pacific carry the same legacy of industrial chemistry that has reached every other Hadal zone on the planet. Microplastics have been found in Hadal sediments across multiple trenches, including in the broader Izubonin region. Plastic fragments and fibres have been recovered from amphipods collected at depths that seemed, until recently, too remote for human refuse to reach. There is something quietly unsettling about this. Not in a dramatic way. The trench is not dying, the amphipods are not vanishing, and the deep ocean is not in immediate crisis in the way that shallow coastal ecosystems sometimes are. But the fact that a place this remote, this inaccessible, this genuinely difficult for humans to even observe, let alone visit, has already received a measurable chemical signature from the surface world. That is worth sitting with for a moment. It reframes the idea of the trench as an untouched wilderness. It is not untouched. It has been absorbing the outputs of human industrial civilization for decades, passively, invisibly, without any deliberate decision to expose it. The pollutants did not arrive because anyone chose to contaminate the Ogasawara Trench. They arrived because the ocean is connected, because water circulates, because particles sink, because animals eat and die and fall. The trench is downstream of everything in a sense. It receives what the surface sends, whether the surface intends to send it or not. This does not mean that the trench's biology has been fundamentally altered by contamination. The amphipods carrying PCBs in their tissues appear, from available observations, to be functioning normally. Whether those chemical loads affect reproduction, immune function, or long-term population health is not known. The studies that have been done measured contamination levels. They were not designed to assess biological effects. That research has not yet been done in any systematic way for hadal organisms, partly because getting enough specimens for a robust toxicological study is itself an enormous challenge. What the contamination data does tell us is something about the reach of human activity. The Ogasawara Trench sits nearly 10 kilometers below the surface of the ocean. It is one of the most physically remote environments on this planet. A human being cannot survive there without protection that would require years of engineering to develop and billions of dollars to deploy, and yet the chemical record of 20th century industrial production is already present in the tissues of animals living at its deepest points. That is a remarkable statement about scale. Not a comfortable one, but a remarkable one. There is also the question of what the trench has absorbed from the surface in terms of organic material connected to the war years and the decades that followed. Whale populations in the Western Pacific were heavily depleted by commercial whaling throughout the 20th century, which reduced the frequency of whale falls, those large food pulses that sustained deep communities for years or decades. Whether this affected the ecology of the Ogasawara Trench's hadal zone in any measurable way is genuinely unknown. The connection is plausible, but not documented. It is the kind of indirect human effect that is almost impossible to trace in a place where the baseline ecology was never recorded. The fishing industry has also operated intensively in the waters above the trench for generations. Japanese fishing vessels have worked the Izubonin region for centuries, and the industrial-scale fishing of the 20th century dramatically reduced populations of large pelagic fish, tuna, billfish, sharks, that once moved through these waters in large numbers. When these animals die naturally, they sink. A dead tuna at depth is a food resource for deep-sea scavengers, including the amphipods and other hadal organisms that depend on organic material falling from above. Whether the reduction in large pelagic fish populations has meaningfully reduced the organic flux to the trench floor is, again, a question without a clear answer. The trench's food supply was never measured before industrial fishing began, so there is no baseline against which to compare the present. What all of this adds up to is a picture of a place that is simultaneously one of the least known environments on Earth, and one that has already been touched, in multiple ways, by the human world. The wartime losses, the post-war dumping, the industrial chemicals, the microplastics, the indirect effects of fishing and whaling. None of these arrived at the trench with any intention of reaching it. They arrived because the trench is part of the same ocean that covers most of this planet, connected to the surface by water and gravity, and the slow circulation of matter through the marine system. In a way, this makes the trench more interesting, not less. It is not a pristine laboratory sealed off from the world. It is a place that has been shaped by geology for millions of years and by human activity for decades, and the interaction between those two timescales, the geological and the industrial, is something that science has barely begun to examine. How do organisms adapted to extreme pressure and cold and darkness respond to novel chemical compounds that have no natural analogue in their evolutionary history? Nobody knows. The experiments, in a sense, are already running. The results have not been collected. The human record layered into the Ogasawara Trench is not written in any archive or database. It is written in sediment and in the tissues of small crustaceans at 9,000 meters, in the slow corrosion of steel somewhere on the abyssal plain, in the chemical signature of compounds that were manufactured in factories and used in products, and eventually, through a long chain of transport and transformation, came to rest in one of the deepest places on Earth. It is a strange kind of record, unintentional, incomplete, but real, and it sits alongside the biological record, the amphipods and the polychaetes and the possible undescribed snailfish and the dark biosphere in the sediment, as part of what the trench actually is, not just a geological feature, not just a biological frontier, but a place where the deep history of the planet and the recent history of human civilization have both left their marks in very different ways, at very different depths, over very different timescales. The trench holds both of these things at once, the ancient and the recent, the undiscovered and the already contaminated, the entirely unknown organism and the entirely familiar chemical. That combination is, in its own quiet way, one of the more honest portraits of what the deep ocean actually represents in the world as it exists now. Not a wilderness beyond human reach, but a place that human reach has already exceeded, even before human understanding has caught up. Which makes what remains unknown there all the more worth pursuing. The contamination does not cancel out the discovery. The PCBs in the amphipods do not make the unidentified fish in the lander footage less significant. If anything, the fact that the trench has already been touched by the surface world makes understanding what lives there, what has survived there, what has adapted there, what is still waiting to be found there, a more urgent question than it might otherwise seem. And that question, the biological one, the one about what the trench still hides, opens out into something larger, into what the future of deep ocean exploration might actually look like, and what tools and intentions might finally bring the Ogasawara Trench into clearer view. So that is where we arrive, not at an answer exactly, more like a clearing in the middle of a very long forest, a place where you can stop and look around and see how far you have come, and also see how much is still in every direction around you. The Ogasawara Trench is, in the most straightforward terms, one of the deepest and least explored places on this planet. It runs for roughly 1,000 kilometers south from the waters near Tokyo Bay, dropping in places to nearly 9,800 meters below the surface. It is the product of a subduction zone that has been operating for tens of millions of years, where the Pacific plate slides beneath the Philippine sea plate at a rate of a few centimeters per year, slow by human standards, but relentless by any other measure. The trench is not a passive feature. It generates earthquakes. It shapes the volcanic island chain above it. It creates conditions at its floor that are among the most extreme sustained environments on Earth. Pressure approaching 900 atmospheres, temperatures barely above freezing, total darkness, and a chemistry shaped by the slow release of hydrogen and methane from the rocks themselves. What lives there is only partly known. Amphipods, certainly. Those small shrimp-like crustaceans that swarm bait in the lander footage and have been recovered in samples from around 8,500 meters. Polychaete worms. Sea cucumbers moving slowly across sediment that is mostly fine clay, and the compressed remains of microscopic organisms, foraminifera, almost certainly snailfish of some kind, though whether the Ogasawara Trench hosts its own distinct species, separate from the pseudo-Liparus swirei confirmed in the Mariana at 8,178 meters, has not yet been established. There have been elongated fish observed in lander footage from the Izubonin region that have not been formally described. There have been holothurians moving in ways that surprise the researchers watching the footage. There is a dark biosphere in the sediment, microbial communities living not just on the surface of the seafloor but within it, possibly representing a significant fraction of the total biomass in the trench, almost entirely unstudied. And there is, almost certainly more. The logic of Hadal endemism, the pattern by which each trench acts as its own evolutionary island, isolated from other trenches by abyssal plains that are too shallow for the most pressure-adapted organisms to cross, suggests that the Ogasawara Trench contains species found nowhere else, species that have been evolving in isolation for long enough to become genuinely distinct. The genetic studies done on amphipod populations across different trenches have already shown that the Izubonin populations are not the same as the Mariana populations or the Kermadec populations. If that is true for amphipods, which are among the best studied Hadal organisms, it is likely true for other groups as well. The trench almost certainly holds undescribed species. The question is not really whether they exist, it is when and whether we will find them. The tools available right now are limited in ways that matter. The Shinkai 6500 Jamstek's most capable crewed submersible can reach 6,500 meters, which is deep, genuinely deep, but not deep enough to reach the Hadal portions of this trench. The Kaiko ROV, which could reach full ocean depth, was lost in 2003 when its tether snapped during a typhoon. Freefall landers, the uncrewed camera and trap systems that are dropped from a ship and sink to the bottom under their own weight, have been the primary tool for Hadal biology in this trench, and they have produced real data. But a lander sits in one place. It shows you a small circle of sea floor. It captures what comes to the bait. It cannot follow an organism, cannot explore a ridge, cannot look inside a crevice or collect a sediment core from a specific location of interest. The coverage is minimal. The trench floor, below 6,000 meters, spans roughly 9,500 square kilometers. The area that has been directly observed is a fraction of that. What changes this, or what might change it, is a new generation of vehicles designed to reach full ocean depth. The DSV limiting factor, the submersible used in the 5 Deeps expedition, which completed dives to the deepest points of all 5 oceans between 2018 and 2019, demonstrated that full ocean depth crewed diving is now technically possible with modern materials and engineering. Triton Submarines, the company that built the limiting factor, has continued developing full ocean depth systems. Jamstek has announced plans for a new generation of deep-sea research infrastructure, including vehicles and lander systems capable of reaching the deepest parts of the trenches in the Western Pacific. These are not distant science fiction. They are engineering programs in progress, with timelines measured in years, not decades. When those vehicles reach the Ogasawara Trench in earnest, when a submersible can spend hours on the floor at 9,000 meters, moving slowly along the sediment, equipped with high-resolution cameras and manipulator arms and sample containers, the biology of the trench will change from a set of educated guesses into something more like a real picture. Not a complete picture. The trench is too large and too complex for any single expedition to resolve, but a real one. The kind where you can say, with confidence, here is what lives here, here is how it is distributed, here is what is endemic and what is shared with neighbouring trenches, here is the structure of the community at different depths along the trench's walls. That moment has not arrived yet, but it is closer than it has ever been. In the meantime, there is something worth sitting with. The Ogasawara Trench has existed in something close to its current form for millions of years. The organisms living at its floor have been there, in one form or another, for longer than modern humans have existed. The trench did not wait for us to discover it. It was not holding its breath. It has simply been there, deep, dark, cold, pressurized, alive in its own way, while the surface world changed around it. Ice ages came and went, sea levels rose and fell, the islands above the trench were built by volcanoes and then worn down and then built again. Human beings arrived in the Pacific, spread across its islands, built civilizations, fought wars, industrialized, and eventually began lowering cameras and traps into the water to see what was there. The trench received all of this with what you might call indifference, though indifference is probably too active a word. it simply continued to be what it is. There is something in that which is genuinely calming if you let it be. Not every place is waiting to be understood. Not every depth is waiting to give up its contents. The Ogasawara Trench is not a mystery that wants to be solved. It is a place that exists on its own terms, at its own depth, at its own pace, and the fact that human understanding has not yet caught up with it is not a failure. It is just a description of where things stand. The ocean is large. The deep ocean is larger than most people imagine. The Hadal zone, everything below 6,000 metres, covers an area roughly equivalent to Australia, distributed across the trenches of the world, and of all of that, almost nothing has been directly examined. What the Ogasawara Trench represents, then, is not just a scientific frontier in the narrow sense. It is a reminder that the Earth is still, in meaningful ways, larger than our knowledge of it, that there are places where the questions outnumber the answers by a very wide margin, where the creatures that live there have never been seen, never been named, never been placed in any taxonomy or described in any paper, where the chemistry of the sediment has not been fully characterized, where the effects of this surface world, the chemicals, the plastics, the reduction in whale falls, the centuries of fishing, have not been traced or measured. All of that is genuinely unknown, not approximately unknown, not mostly understood with a few details remaining, genuinely fundamentally unknown in ways that would surprise most people who think of the ocean as a well-studied place. And there is value in that. Not just scientific value, though there is plenty of that. The biology of Hadal organisms has already produced insights into pressure adaptation and protein stability that have applications far beyond marine biology, but a quieter kind of value too. The value of knowing that the world is still larger than the map, that somewhere, right now, at 9,000 meters below the surface of the Western Pacific, there are creatures moving through the dark that no human being has ever seen. That they are going about whatever it is they do, feeding when food falls, waiting when it does not, living according to pressures and temperatures and chemical gradients that would kill any unprotected surface animal in seconds, without any awareness of being unknown. They are not waiting to be discovered. They simply are. That is a quiet thing to think about at the end of a long day, or late at night, or whenever you happen to be listening to this. The world is still, in places, beyond reach. And that is not a problem to be solved so much as a fact to be appreciated carefully before the next expedition goes out and brings a little more of it into view. The Ogasawara Trench will not stay unknown forever. The vehicles are being built, the surveys are being planned. The science is moving slowly and carefully toward the floor of that long, narrow, ancient cut in the Pacific seafloor. What it finds there, what names get attached to what creatures, what chemical gradients get mapped, what evolutionary stories get told, will add something real to what humanity knows about this planet. That is worth looking forward to. But for now, the trench is still there, still deep, still largely unread, and that in its own way is enough. Thank you for spending this time here. If you found this journey worth taking, a like means more than you might think, and subscribing means you will be here for the next one. We will be back going somewhere else that is quiet and deep and worth understanding slowly. Until then, wherever you are, whatever the hour, rest well.